all the Randall that you can handle. Obviously, Randall is besties with Joe Rogan. That's how I came across him originally. This man is insanely intelligent and super kind and a real inspiration, because I found out yesterday that he is self-taught. The guy studies every day. I think he reads like 3 papers a day, which is phenomenal. But that's a real inspiration for people like me or anybody out there, just to say that if you got a brain and you apply it, like, look where you can go, look what you can achieve. He grew up on both ends of the Mississippi, and he is an on-the-ground expert on the scablands. And he's a pre-Google archive collector. It's so easy for me or anyone else to just Google things today. And with ChatGPT, that's about to get insanely easy. This guy, since the 70s, has been analog. He's got all of his research in paper, which is just phenomenal. He's a geometrician, an independent researcher, the rock dude, or equally the dude that rocks, the guy that really needs almost no introduction. It's Randall Carlson!
Thanks. Yeah, it's great to be here. I've been looking forward to this for months. I didn't really necessarily believe George when he told me it was going to happen, but then I just decided I'd show up anyway, and then there was all these people here, so they said, I guess it's going to happen. So there's the man himself.
Ye of little faith.
No, I tell you, George and I have become great friends in the last few years. And I knew about George actually long before I met him, because he was the guy who I'd been getting into the Younger Dryas stuff and Carolina Bays and all of this, and then I discovered the cosmic tusk. I thought, who's this guy that seems to know as much as I do about this stuff?
That was exactly my reaction.
Yeah.
You went on to become famous.
I'm not sure about that, but I tell you what, I can say this. I think today I have set a world record in terms of how many times I've had my picture taken. So I don't know if that bodes good or evil, but I think it's probably good.
That's great.
Yeah.
Thanks for taking the time. Right, everybody?
Oh, I'm looking forward to this. I got some... I would recommend it if you're easily triggered. You probably should take your exit right now. So is Chris Cottrell, are you still here, Chris? Or did he bail out? Okay, I guess he's gone. I had one clarification. See, when I got into this, my shift, people say, well, how do you characterize yourself, or how do you classify yourself? And I usually say, well, that's a good question. I would call myself a catastrophist, or a cosmographian, in the sense, the Renaissance sense of somebody who's just interested in everything. And that's my problem, has always been interested in too many things for one lifetime. That's become clear to me at this point. So if anybody has the secret of the Philosopher's Stone, please fill me in on it. But I think it was 1979, I was 78, 79, right in there, back in the kind of the hippie days. People were always talking about Atlantis and stuff, and I didn't have a big interest in Atlantis. And I finally thought, well, I'm going to look into this and see what there is to it. So I got a couple of books, actually 4 or 5 books. Read the most famous maybe is Ignatius Donnelly, his book on Atlantis, the antediluvian world, and then I think the follow-up was Ragnarok, the Age of Fire and Gravel. And of course, he gets always attacked by the mainstream guys. How many of you watched Ancient Apocalypse with Graham? Yeah. Now let me ask you a question, okay? Now, there was a lot of folks watch Ancient Apocalypse here. How many of you, now I don't know how many of you actually read many of the attacks and critiques of the show. I went through about 9 or 10 of them, right? Now here's the thing that I was wondering. Now, all of you folks that here watched it, how many of you, your takeaway from it was that Graham Hancock is a white supremacist? If that was what you gleaned from that show, raise your hand. However, isn't it strange that every archaeologist and journalist that seemed to cover that in the mainstream media reported that over and over and over again ad nauseum? Every single one. He's a white supremacist, a racist, etc. Never mind his beautiful wife, Santha, who is a woman of color and just a wonderful woman. I've had the opportunity of traveling with them and sharing adventures with them, and I know Graham well, and I'm thinking to myself, to call that man a white supremacist, there's something very, very wrong here. I mean, there is, yes. Anyways, I just thought I'd say that. Going back to the 1970s, when I kind of shifted over into really trying to understand the history of this planet. That was my early obsession, and it sort of, I blame it on my upbringing in rural Minnesota. We were right at the margin of what was called the superior lobe of the Laurentide ice sheet. Of course, I didn't know that back then. All I knew was I was fascinated by the hills and the valleys and the lakes everywhere, and I do remember my father showing me a book out of a picture when I was maybe 7 or 8, and it was a picture showing the great ice sheets, and he said, yeah, there was a big glacier here at one time, and it might have been like thousands of feet deep right here where we live. And that just really, that stuck with me. And then in 1969, there was a place on the bluffs overlooking the Minnesota River, which is a tributary to the Mississippi, just south of Minneapolis. And I didn't know this then, but the modern, and I'm going to show you a slide of it a little bit into the program here, that the Minnesota River Valley was carved by the draining waters of Lake Agassiz. If you've ever heard of Lake Agassiz, it was a gigantic inland freshwater sea that was formed from meltwater of the Laurentide ice sheet melting. So I had no idea of this, but I remember there was, it was called Flying Cloud Airport, and I've told this story before, but people always keep asking me, how'd you get into this, how'd you get into this? So I was just out of high school, and I remember they used to have free rock concerts there on the bluffs, and I just wandered away to take a break from the music or whatever, and I remember standing there on these 200-foot high bluffs, and I could see the little ribbon of the Minnesota River there down below me. 3 miles on the other side, there was another set of bluffs, like the ones I was standing on. And I'm just kind of like looking back and forth and looking up and downstream and looked at that modern Minnesota River down there, and I kind of looked at it had its own little banks and a modern floodplain, and I just had this sort of intuitive feeling that I was actually looking into the bed of a giant river. And it kind of made its impression in my mind, and then I rapidly forgot about it because there were a lot of other things going on in the world and my life at that time. But it kind of went into my subconscious, where it kind of marinated for a few years. And I began thinking about it, maybe by the mid-'70s, when I really began to go, I know there's a story here. And the summer of '70, next year, I spent the whole summer traveling around all of the not all, but most of the western states, camping and hiking and just exploring, sometimes by myself, sometimes with a friend or two, and seeing these spectacular landscapes. And I remember one day, we was with a friend of mine from high school, and we were driving through the Columbia Gorge. And you had the Hood River and the John Day River and these rivers coming in, tributaries to the Columbia. And I just remember this feeling, this sense I had as we're driving through there, that like I was some kind of a microbe and I was looking at this gigantic landscape. And it really impressed me. And I would say that it was at that summer of '70 where I really took an interest in geology. And so I started procuring a few books here and there. And then fast forward, like later on in the '70s, returning back to this Atlantis idea, I thought, well, I'll look into that. And, there was a lot of fringe stuff. But there was a couple of books, one by Otto Mook, and in that book, I believe it came out in 1979, he was a German physicist. He had a chapter in there that he was exploring the possibility. His theory was, interestingly, that the whole scenario was triggered by a bolide impact. And he theorized that the bolide was 5 to 6 miles in diameter, which, interestingly, a year later, when the Cretaceous Tertiary impact event was first proposed, it was a bolide about 5 or 6 miles in diameter that would have deposited the layer of iridium worldwide. But anyways, he had a section in there on the Carolina Bays. And I had never heard of the Carolina Bays before then, but he talked about the Carolina Bays, and I thought, well, gee, this is right in my backyard. So I started getting interested in the Carolina Bays, and then, I didn't have the resources then. I was, working, trying to establish my design build business. And it was only, I would say, at about the mid-'80s where I actually began to go out in the field to explore the Carolina Bays firsthand. I remember seeing the images from the air, and they were very impressive, but then when you see them from the ground, they're not so impressive, really, because a lot of them are just swamps. You can't tell that they're elliptical formations. That was the famous, I think, I missed the first few minutes of Chris's discussion, but I think he did talk about the first maybe aerial survey, Fairchild aerial surveys. I think it was in 1933, and in the New York office, when they were assembling the mosaic, that was the first time they it popped out and I saw these elliptical features. So I got really interested in the bays, and back then, you didn't have the internet, so I would go to the libraries of Georgia Tech, Emory, the Fernbank Science Center, and I got a hold of the book, The Mysterious Carolina Bays by Henry Savage, and I think it came out 84, 85, somewhere like that, so that would have been probably just newly published when I got my hands on it. I read it. His conclusion was that it was a fragmented comet. And then I do remember that it had a very extensive bibliography, and I was so interested in this that I set out to try to procure as many of the papers as I could, going back into the history of it. So I went back to, did Chris mention Melton and Schreiber? Melton and Schreiber, okay, maybe he didn't get into that level. But yeah, so I began reading all the papers, and it seemed to me at the time, because now by this time I had begun to become familiar with the Tunguska event of 1908, which I'm sure all of you are somewhat familiar with that event. And I began to think, well, is it possible that there would have been thousands of Tunguska-like events happening like this? And I just didn't know. I didn't know enough to have an opinion on it, and I still don't really, to tell you the truth. Like Chris says, I'm still kind of on the sidelines waiting to see if there's some more definitive evidence that comes in. But in any case, I remember sitting there one day, and it was mid-'80s, and I had also, one of the other books I had read on Atlantis was called, doesn't matter what it was, by an author named Cedric Leonard. And he had a chapter in there that was entitled The Catastrophe of 10,000 BC. Now, he didn't mention Carolina Bays, but he did mention the Missoula flood, or floods, that occurred and created the channel scablands. So this was the first place I'd heard about those. And as I was reading that, I think, well, in my travels in 1970, I went across that landscape, and I saw some impressive stuff, but I didn't see something that stuck with me like what I saw in the Columbia Gorge. However, now what I obviously know is that those land features in the Columbia Gorge were the byproduct of these gigantic mega floods that happened. So anyways, it was those two books that really sort of cemented my interest in catastrophism. So I go, well, I want to go and see what hard science has to say about this. And that was when I began to really do spending all my spare time in libraries. And I formed a relationship with the librarian at the Fernbank Science Center that had set up a science library available for the public, but nobody hardly used it. So I went in there and I showed her what I was doing, and she got really interested. So I was able to procure, for a couple of years there, we had this network going out where, she was reaching out, they were interconnected to the interlibrary loan. So that was very, very helpful for me to get things that weren't readily available So I just began to dive into the literature, and I think maybe 2 to 3 articles every day is what I consumed for years. And then, of course, once we got digital files available, I kind of have shifted away, and I don't really have to spend much time actually physically going to a library anymore, because I find most of it online, and I pay money and whatever to have passwords and accessibility. But anyways, I remember one day I'm sitting there and I'm looking at the orientation of the bays in North and South Carolina, and very roughly the long axis of the bays points about 45 degrees. It's about on a 45-degree angle southeast to northwest. So I thought, if this was a fragmenting comet, I started thinking about visualizing the scenario of how it would have evolved and where the thing would have come from and broke up. And I thought, okay, what it seems to be telling me is that the Earth encountered a swarm of stuff. And now, of course, this is post-1980, so the, excuse me, I usually go through this whenever I give a lecture, like 5 minutes in. I have to clear my throat, so I'll do that right now. So here was my thinking. If it was a comet or a bolide or fragmenting asteroid, whatever, it looked like from the orientation, and Chris probably mentioned this, that there are prominent sand rims on the southeast quadrant of the bays. Did he mention that? Okay, so which would have looked, and it sort of implied that if it was an incoming object, it was coming from the northwest at a low angle. And so I thought, okay, if this is going, in Henry Savage's book, he's basically assuming that it's late Pleistocene, that the formation of the bays was late Pleistocene. So I started thinking, well, if late Pleistocene, most likely the great ice complex was in existence. So is there any evidence that of anything unusual happening to the ice sheets? And then I remembered back to Cedric Leonard's book and the reference to the catastrophe of 10,000 BC. So I went in and I started looking at, well, what I did was I first really focused in on the channel scablands and the work of J. Harlan Bretz. And Bretz was a geologist. When he first discovered the existence of these mega features in eastern Washington, it was 1910, and he was a high school science instructor. He later became a full-fledged geologist, and eventually was awarded the Penrose Medal, which is the highest honor in the geological profession. But anyways, I then this time I kind of know how to work my way around a library, so I went in and I started going through all of his early papers, one by one. I took them in order, so I could kind of get the sense of his evolving thinking about it. His first paper that specifically focused on channel scablands and the idea of a megaflood was 1923. His last paper was 1969. And in there was probably a dozen papers that showed the evolution of his thinking. So I worked my way through all of those papers. Finally, I got the resources. 98, I'd been thinking about wanting to get out and see all of this for myself. So in 1998, my friend, Brad, are you in here? My friend Brad Young? Is that you way back in the corner, Brad? I want to make sure that Brad gets the credit that he's due, because I met Brad has been my partner in this work, helping me or getting organized, doing all this stuff for over a quarter century now. And we've had some great times together. And you know what? We haven't had a single argument, have we? So we're overdue, but but yeah, so in 1998, Bradley and I organized a little trip with 2 more buddies, and we went out and spent a couple of weeks exploring the scablands of eastern Washington, and I had all of Bretz's papers and other papers that had been published, and I was duly impressed by what I saw. And I've lost count of how many times we've been back. He and I have done I've really literally lost count of how many trips we've done around, we're trying to take in all of North America. And as we see when we go through this here, you're going to see that I think the evidence points to the conclusion that whatever this catastrophe was of the terminal ice age, North America was ground zero. And South America was very close behind. And one of the yardsticks that I've used to try to get some sense of the magnitude of a catastrophe is based on species loss, because particularly megafaunal species. And I think you've heard on several occasions here, I think Mark this morning commented some on megaspecies loss. I think he said there was 50 genera. It's over 100 species that have been lost at the end of the last ice age. And, at the time I first started researching that, the dominant theory was that they were hunted to extinction. But the more I began to learn, the less plausible that seemed to me. And so, okay, so maybe there were 3 cases where mammoth skeletons were actually found with Clovis points embedded in the rib cage and so on. So clearly looked like they hunted mammoths. But then I began to really look into, okay, how many? What was the census of the number of mammoths alone? And it turned out to be somewhere around 10 or 12 million, the estimates that I saw for the total number of proboscidean species on Earth, which is, long nose. So very few people realize that right here in this area of the country, there were 3 species of proboscideans, or, elephants, if you want to use the more vernacular term. So if, like at lunch, if you're going out for your break or whatever, and this was 15,000 years ago, there may have been mastodons or mammoths roaming around, sharing your space while you were eating lunch, which probably would have been just fine. But if there were dire wolves and saber-toothed cats, you probably should come back inside. So anyways, I kind of began to get skeptical about the idea that hunters, okay, maybe they could eliminate one species, but over 100 species worldwide. So as I learned more, I realized that North and South America shared about the same magnitude of species loss, megafaunal species. Now, I will define megafaunal as an animal that weighs over 44 kilograms, which is about 100 pounds in body weight. So from that basis, I'm estimating that most of us in here are megafaunal mammals. Although I did see some little ones that are probably not quite there yet. But anyways, I began to look into, what are the estimates of the world population during the late Pleistocene? And the numbers that kept coming up was between 5 and 10 million people worldwide. And I started thinking, now is this plausible that if you've got a total population, let's say of 10 million people, and you've got 10 million mammoths, of the 10 million people, how many of those are actually out hunting mammoths? Because that's everybody, the elders, the children, the men, the women, and I'm assuming then that probably most of the hunters were men, although I think there's some evidence that women were also really prolific hunters as well. But given the nature of the environment, it was probably fallen on the shoulders of men to do most of the hunting. So I started thinking, well, if the total population is 10 million, how many are actually out hunting mammoths? Is it 3 million, 4 million? And how does that square with the idea that somewhere around 10 million mammoths went extinct within a very short period of time? It just didn't add up. Then when you add in the giant beavers and the giant ground sloths and the American Pleistocene lion and the giant short-faced bear and the cave bear and all the rest, the giant camels that used to inhabit the American Southwest, it just didn't add up. And I thought, God, there's got to be another explanation for that. And so I kept going back to the idea of catastrophe. It's got to be some kind of catastrophe. And then, of course, that also was consistent with a lot of the mythology and legends and things that I had been reading, because that was another area of fascination of mine, was stories from old. And over and over and over again, you read these stories about the great floods and fires and destructions. Luke this morning was talking about the Mayan traditions, and of course the Mayans have very rich catastrophist traditions. And it began to dawn on me that, maybe we should look at these as not just, the pre-scientific, illiterate ravings of barbarians, but maybe there's actually real information that can be extracted from these stories. And of course, in the interim, I still now firmly believe that the legacy that we've inherited from ancient peoples can be very instructive and insightful in coming to terms with some of these past events. And so, anyways, now going back to the Carolina Bays, and I'm thinking, okay, so if we have these, if we have and I'm not saying from this that I now believe that this is what happened. I'm wide open to that, but I just don't know. That's why I was very interested in Chris's very excellent summation of the theories. I've met several of I've met Davies and Antonio Zamora. I've had the chance to see their presentations firsthand. I'm not making up my mind. I'm still sitting on the fence, waiting for something more definitive. But what it did do was it led me to this study of the great meltdown, I call it, of the ice sheets. And it started with the scablands, and then it quickly expanded from there. Now, I did say that I thought North America was ground zero, and I base that on species loss. Particularly, we're looking at megafaunal species loss. Megafauna require a lot more habitat, intact habitat, than smaller species. You know, if you look at mammoths, obviously, you know, you're talking 5 or 6 tons. They have to eat an enormous amount of food every day to live. The generational turnover time is much longer. The nurturing of young is much longer. So if you destroy habitat, the smaller species are going to have a greater propensity for survival than the larger species that are depending upon a relatively stable habitat and food supply. And so I began to think, well, it looks like maybe we could use species loss as a yardstick to understand the severity of the catastrophes. And so North America and South America both lost about 75% of their late Pleistocene megafaunal species. Eurasia lost about 30, I think the estimates are about 34 or 35%. Africa has only lost 10%. And that's, and that's one reason why Africa has large animals today, has a proliferation of megafaunal species, because a lot of those species are actually Pleistocene megafaunal species. So Africa lost about 10% of the megafaunal species. So what this is showing us is that the catastrophe was not uniform around the planet. It seemed to impact some areas more severely than other areas. And that would not be inconsistent with an idea of a bolide or a multi-bolide impact. If you have a rain of things from the sky, and of course the Earth is turning on its axis, so you know if you have a short-lived period of a number of hours, 6 or 8 or 10 hours, it's going to be concentrated on one side of the planet. So anyways, Bradley and I, with some other friends, began doing regular tours exploring the scablands, and one of the things that I began to conclude was looking at this, just like I didn't think the human overkill hypothesis added up for the extinction of megafaunal species, I started thinking that the explanation for the formation of the channel scablands didn't add up. And it just, I couldn't make an argument back then for it. I can now, and I'm going to make that argument somewhat here in my presentation tonight, that the current model suggests that there was a very large proglacial lake in the valleys, the mountain valleys of western Montana. And going back to an original idea that was actually proposed by T.C. Chamberlain in the 1890s, he was a geologist who did some traverses of that region out there, and he saw shorelines up on the mountainsides. And he concluded that those were shorelines. The technical term is strand lines. He saw the strand lines up on the hillsides, and he based upon the fact that there were many proglacial lakes forming in the 19th century, because you may or may not know this, that throughout the entire Holocene, the largest glacier mass was actually within the last millennia during a period called the Little Ice Age. And this is has been determined because you can study terminal moraines, which is the material that forms on the terminus of a glacier lobe, and that material can be dated because there's often datable material within the moraines, but those terminal moraines from the Little Ice Age glaciers were the largest typically around the planet since the end of the Great Ice Age. And we now know that there was a period in the early Holocene that used to be called the climatic optimum, but I think they changed it to the hypsothermal because the implication of climatic optimum was that when you had a world that was 1 to 2 degrees warmer than now, that was the optimum temperature. And that didn't quite square with some of the scenarios that were coming along, in the 90s and 2000s and so on. So anyways, we went out there and I arranged to have an interview with Roy Breckenridge, because one of the things I wanted to do, and I'm going to show you this in a slide in a minute, is that the theory was that there was this giant glacial lake. The high water mark was defined because the highest strand line was 4,200 feet above sea level. And since then, there's been traces of a strand line that have been found 50 feet higher than that. So some of the maximum volume of the lake has been revised upwards to where now it was over 600 cubic miles of water. That's a hell of a lot of water. Okay, so if you follow the route, the idea is, and you'll get to see this on the map here in a minute, you had these large basins, the Mission Basin, which was the largest. You had the Missoula Basin, you had the Bitterroot Valley. They all held water up to that 4,200, 4,250 foot strand line. Typically in the Mission Basin, the elevation of the land surface there is about, as well as in the Missoula Basin, where the town of Missoula now is, it's generally around 3,000 to 3,200 feet above sea level. So from that, you can actually measure, if we're 3,200 feet above sea level and the highest strand line is 4,200 feet above sea level, well, you can, then determine that the water was 1,000 feet deep. And sometimes I wonder how many of those students, we've been there multiple times, taking people on tours there, studying it ourselves. Sometimes I see the students wandering around with their books, hurrying from class to class, and I'm wondering how many of them realize that line up there on the hill is actually that there was a lake, and they would have been at the bottom of a 1,000-foot deep lake if they were here, a few thousand years ago. Well, 12, 14, 15,000 years ago. But anyways, here was the general scenario, and T.C. Chamberlain proposed this, that there was an ice dam somewhere to the west, and he was very non-definitive about where that would have been. Then there was a geologist working for the U.S. Geological Survey named J.T. Pardee, Jonathan Pardee, and his very first paper that he ever wrote was called Glacial Lake Missoula, because he had followed up from the hints of T.C. Chamberlain, and he had seen those strand lines himself. So he was the first one who wrote this paper on Glacial Lake Missoula. It came out in 1910, right? He kept studying the lake, but he never published on it until he actually retired from the Geological Survey, I think it was 1943. And he published his final paper. So his career spanned 30, 32, 33, 34 years. His very first published paper, Glacial Lake Missoula, his final paper after he'd retired from the Geological Survey was entitled Unusual Currents in Glacial Lake Missoula. So this was an interesting title. What did he mean by unusual currents, right? Well, he had seen, by this time, which was not reported in his 1910 paper, he had discovered the existence of gigantic current ripples. And I'm going to show you a couple of examples in slides here. He discovered the presence of these gigantic current ripples in a place called Camas Prairie. Now, we're going to be doing a tour this September of the western Montana region of Lake Missoula. So one of the places we do visit is this Camas Prairie, where people can see for themselves a massive field of these giant current ripples. At the north end of the basin, the current ripples are the largest, and then they diminish over a distance of about 5 or 6 miles to the south. At the northern end, the ripples, the amplitude of the ripples is as much as 30 to 50 feet. So you figure this room here is probably 20 feet from the floor to the ceiling. Now, 20 feet, imagine a current ripple, like the kind you would see at a beach or a sandbar along a creek. But this darn thing is 40, 50 feet high, 200 to 300 feet wavelength. So this is what Pardee had discovered after his first paper. So he assumed, he came to the conclusion that whatever constructed those gigantic ripple fields, current ripple fields, had to be unusual. So that's why he called the paper Unusual Currents. But the other thing he discovered was the floor of a lot of these valleys had evidence of massive currents because there would be layers of huge boulders on the bottoms of many of the valleys and things where the water had been and where the water had moved. So back to J. Harlan Bretz now, he's been studying the evidence of these tremendous erosional events in eastern Washington, and he is getting absolutely no support from his colleagues who are thinking he's a crackpot. And there was a concerted effort to try to suppress his ideas or to at least counteract them because he was actually getting published in some of the mainstream geological journals, the Journal of Geology, Geology itself, several of the other major mainstream publications were publishing his work. But the opposition was led by a geologist by the name of James Galooly, who set out with the goal in mind of suppressing this heresy because you can kind of understand. They were like, okay, you're talking about these gigantic floods. Basically, what you're going to do now is you're going to give ammunition to the biblical literalists that are going to now claim this is Noah's flood, and we just went through 100 to 200 years of trying to get away from the religious authorities to have the freedom to, explore science wherever it leads us. And now here's this guy, J. Harlan Bretz, who's trying to drag us right back to biblical literalism and Noah's flood. So you can kind of understand where they were coming from. So they set out under the leadership of James Galooly to try to suppress this heresy and be done with it. So what they did is they invited Bretz to Washington, D.C. for a conference, which was going to be Bretz's colleagues and peers going to be there, as if they were going to give him a fair hearing. But really it was an ambush. They were going to basically do everything they could to discredit Bretz, to discredit the hypothesis. Of course, most of them had never actually been out and seen the evidence in the landscape for themselves, okay, including James Galooly, because they felt confident that they could explain whatever Bretz was describing as being the cumulative effect of, thousands and hundreds of thousands, even millions of years of erosion. Another one, the opposition to the flood was Richard Foster Flint, who was actually a great geologist and wrote great papers on glacial geology and stuff, but he was also opposed to the idea of megafloods. So anyways, in attendance at this meeting was J.T. Pardee, who was at the time about to retire from the survey, but I don't think he had yet. And in fact, he had gone earlier to his boss at the survey saying that, he had this evidence in hand that about this Great Lake. And it was suggested very firmly to him that he should probably not publish on it. So he didn't until he retired, and that was when he wrote his last paper. Anyways, he's sitting there at this conference in Washington, D.C., and Bretz makes his case, and then everybody in turn goes around and tries to shoot it down. Pardee is sitting there listening intently to what's going on, and then the conference concludes, everybody's getting up to leave, and see here is the primary objection, is that Bretz's critics said, okay, so you say there was these gigantic floods, right? Now, Pardee, when he wrote his paper, Unusual Currents, he used a well-known engineering formula for calculating peak discharge. And he went to a region of the Clark Fork River where you've got a nice straight section of river, and he was able, and by being able to calculate the channel geometry and the gradient, plug it into this well-known formula, and concluded that the peak discharge through there was over 300 million cubic feet per second, which works out to be about 9.5 cubic miles of water per hour. Now that's one hell of a lot of water, right? So anyways, he's sitting there at this conference. The conference concludes. The whole group there has done their best to shoot down the megaflood hypothesis, but then Pardee leans over to one of his colleagues sitting next to him, and he says, I know where Bretz's flood came from. Because see, this was the objection to Brett's was that, okay, you say that these tremendous features were formed by gigantic floods. Well, what was the source of these floods? And Brett's didn't know. I mean, he speculated some kind of rapid warming. Was there volcanoes perhaps involved? All of these got shot down. And so the assumption was, well, if you can't explain where these floods came from, they didn't happen. And that was the gist of what came out of this meeting. So when Pardee leaned over to his colleague and said that he knew where the water came from, that was the beginning of it still took another decade or two for the scientific community to finally begin to accept the reality of these floods. But it almost like provided a sense of relief because, you know, in geology, one of the working tenets of geology is called uniformitarianism. And uniformitarianism is based upon the idea that we try to explain all geological change in the past by reference to things that we can see happening right now today. So if we go out and we study what happens with a river building point bars and eroding its channel, or we see an earthquake or a volcanic eruption spewing out basalt, and you look at things that happen today, you see, you know, a flood, whatever it might be, you see a great fire, and then you look at what it does to the soil, and you can actually, you know, decipher when there were fires in the past and all of this. So the idea was that, and it's a very powerful working tool to understand what happened in the past, but it became dogmatic in that, well, we're only going to accept processes in the past that have modern analogs. So when Pardee made his proposition that there was this great lake held in by an ice dam, they're like, oh, okay, now we've got our uniformitarian analog. Because with those swollen glaciers of the Little Ice Age, as they've been retreating back since the early 1800s, one of the things that they did was they created large numbers of proglacial lakes. These proglacial lakes frequently burst through their ice dams and caused catastrophic flooding. And so the working assumption then became, well, we'll just extrapolate upwards from that, and that's how we'll explain these floods. So the idea became entrenched that there was the giant glacial lake in western Montana. It was held in by an ice dam, and this ice dam finally gave way, and it went from Bretz's initial flood, singular, thinking there was one great flood, in his first paper. By the time he published his final paper in 1969, he was estimating maybe there was as many as 9 different floods. Then other researchers came along, like Richard Waite, and he studied rhythmical layers that were in backflood layers. Because, you know, if you have a flood, think about this. You've got a major big valley, right? And if that valley is working as serving as a conduit for a major discharge through it, right? You've got tributary valleys coming into the sides. So obviously, if the water is filling up the main valley, it's going to backflood into the tributaries, isn't it? Okay, so in the main valley, you're going to have highly energetic flows, picking up sediment, moving sediment, transporting sediment. But in the tributary valleys, the water is going to be backing upstream. It's actually going to be going up gradient. So as it's backing up, what is it doing? It's slowing down. The competency of flowing water to entrain and transport sediment is a function of its velocity primarily. So what happens now is that water backing up, it's laden with sediment, and when it reaches the limit and then essentially stops, and when the water level in the main trunk valley begins to go down, then the tributary valleys that have been backflooded, they will drain out as well. When they do that, they will leave layers of sediment behind. So looking at layers of sediment in a place called Burlingame Canyon Richard Waite determined that there were 39 rhythmical layers, which are now called rhythmites. And in fact, it has been suggested that when we play music with the snakes, we get together, our band that seems to be coming together, we thought we'd call it Randall and the Rhythmites. So be looking for our first record. Should be coming out sometime early next year. Are you here, Russ? Are you back there, Russ? There's Russ, yep. Fellow percussionist back there. Kyle, where's Kyle? Is he here? No? Okay. Yeah, for those of you that watch the podcast, you're going to know that I just cannot resist giving Kyle a hard time. I try. I usually fail miserably. But he takes it. He can withstand the onslaught. Anyhow, so rhythmite layers, there were 39 layers in this place called Burlingame Canyon. Russ, were you there with us when we did our last visit to Burlingame? You were there? Yeah. Oh, yeah. Well, yeah, because you guys, we flew the drones down. We got this awesome drone footage. We had to get special permission because it's on private property, and the owners came out. I think they were really, glad to host us all out there. And it was a great trip. And then we didn't realize it. This was like the next to the last day of this particular trip, and I think we didn't realize it at the time, but we were all coming down with COVID. We got home, and everybody's like, telegram is going back and forth, and everybody is like, But we all survived. And Greg Kagan, are you here? Where are you, Greg? He's out back. Okay, he knew that I was going to call him out. We tried to trace who was, what was it? What do we call it? Patient one or? We were based out of Soap Lake, Washington, in a little place called Soap Lake Resort. We heard after we all left that they had to shut the entire town down. But from what I understand, everybody survived, and they welcomed us back. So apparently, there was no hard feelings. But if there was, I was going to. It's him. It's Greg Kagan. He did it. There he is. There he is, Greg. You've given me a great story, Greg, that I can tell for the rest of my life. How you shut down an entire town. Although we have concluded that he was probably not the only one who brought it. Anyhow, so where was I? 39 layers of rhythmites in Burlingame Canyon. And from there, he concluded that each one of those rhythmites was the result of a separate flood. With the implication, this was the implication, a separate flood. Okay, well, if you have this water filling up these basins in this valley up to 4,200 feet, where the ice dam was, it was actually, the water would have been over 2,000 feet deep. And that was one of the sticky points with me because, as a builder, I knew a few things I'd learned some things about groundwater hydrology. I'd learned things about pressures, things like that. I'd had some engineering. I took some engineering courses in the 70s when I was just launching my business. And that just something didn't seem right to me. That's an awful lot of pressure. In fact, so I did a quick calculation, and 2,000 feet, a hydraulic head of 2,000 feet is going to have pressures of over 950 PSI at the bottom of the water column. And I'm thinking, is that realistic? Anyways, the idea was that there were 39 separate floods with the implication that there were 39 separate fillings of Lake Missoula with 39 dammings of the Clark Fork Valley with glacial ice. And that whole scenario did seem a little bit suspect to me. And I've learned quite a bit since I first started having those thoughts. And I'm more convinced now than ever that that's not the explanation for these tremendous floods, which of course had to have been connected with melting of the ice sheets. Now, I think at this point I'm going to shift over and we'll start looking at some slides so we can get a picture of what the world would have looked like now compared to the way it would have looked at the LGM or late glacial maximum. So you can see there was an enormous mass of ice. Now, to put it into perspective, North America had two great ice sheets. The Laurentide, which was roughly centered on Hudson Bay, and it was about the size of the Antarctic ice cap. Maybe some estimates place it a little bit bigger, the one that now flanks the South Pole. On the western side of the North American continent, starting in Alberta and then going over the Canadian Rockies up into Alaska, was the Cordilleran ice sheet. The Cordilleran ice sheet has been compared to the ice sheet that covers Greenland. Now, in the graphic of the planet that you see on the right, you can also see that there's ice over northern Eurasia. That was usually called the Fennoscandian ice sheet. And during these periods, I think, a number of people were discussing, I know that Chris was discussing the lowered sea level. At the late glacial maximum, actually sea levels got as low as 400 feet below their present elevation. And of course, that was the result of all this, this glacial ice forming on land. So what we've learned, though, is that the rate of melting of the disappearance of this ice really happened much, much faster than previously recognized. And so it leads us to this idea that there was catastrophic melting of the ice sheets. Now, when we go back to the discussion of the scablands, I mentioned James Galooly. He was finally persuaded to get out in the field and look. So there was a group of them that went out, probably would have been the mid-40s, maybe late 40s even. I did know the date, I've forgotten the date. That's not as critical as the outcome of this excursion into the Channel Scablands. And they spent a week going around looking at all of these features. I'm about to show you a few of these features. They ended up at a place called Palouse Falls, which is where one of the great flood streams intersected the Snake River that is flowing up out of southern Idaho, flows through Hell's Canyon, actually reversed the flow of the Snake River over 100 miles when this water hit, but it left this tremendous erosional complex. And in one of the places is this huge bowl with which is called a cataract, and the sculpted landscape around it is almost lunar-like, and this bowl has a plunge pool at the bottom. The modern waterfall of the Palouse River is diminutive compared to this gigantic cataract. And how many of you guys have ever been there? I know some of you that have been on our tours. You know, we always take in Palouse Falls. And so anyways, this was in this trip that Galooly and his colleagues were taking. This was like the last place they visited, and now Galooly has been absorbing all of this suite of different features all week that maybe you could say in isolation, you might be able to concoct a theory of origin, something other than catastrophic megafloods. It's when you get to the whole suite of features that there's just no explanation other than gigantic water flows. So anyways, Galooly walks over. The story goes, and in fact, I think they have a plaque there now, kind of commemorating this event. He walks over to the edge of this gigantic cataract, and he's looking at these features, and he's looking at the little ribbon of the Palouse River coming over the precipice there. It says that he stood there for a long time in silence and then walked back to the group, and he said, exact words, "How could I have been so wrong?" Now that is the way science is supposed to go. Now he did his best. He mounted a challenge against what was an outrageous idea at the time, and he forced Bretts to go back over and over again, just like we saw with the Cretaceous Tertiary idea when it was first proposed in 1980. Well, where's the crater? You know, okay, maybe maybe you have another explanation for the iridium spike, but we're not going to buy into this impact theory until you produce a crater. Well, they eventually did produce a crater, and it's down in the northern Yucatan, Chicxulub. I saw Luke's paper earlier today. He was referencing, his presentation, he was referencing cenotes. Well, cenotes are actually karst-like collapse features that very accurately define the southern rim of this great buried 130-mile diameter impact astrobleme that's under nearly half a mile of post-Cretaceous limestones. And the Mayans, at some point, I would love to give I've done some studies on this, and I plan to get with Luke on this, into Mayan catastrophism. And it seems like they had a very sophisticated knowledge of catastrophism, and they encoded it in their stories, in their, even in the codices. The Dresden Codex, I know Luke is probably well aware I saw it up on the screen, he had it up there, which really does show the combined forces of flood and fire, and really showing the sky god belching out these gigantic floods. And so this was their version of, a Noahide flood. So anyways, the Chicxulub crater was eventually found, and that silenced a lot of the critics. Okay, there it is. Well, let's see, you got to date it. If it doesn't date at the KT boundary, it didn't have anything to do with the extinction of the dinosaurs. Well, they dated it, and it was precisely KT boundary. And it probably wasn't the only impact that happened. And then we find the same thing again repeated with the Younger Dryas impact. Although there's a difference between what happened with the KT boundary and the Younger Dryas, which is this. KT boundary, you're looking at something that happened 66 million years ago, and the Younger Dryas, we're looking at something that happened less than 13,000 years ago. The difference is that humans were obviously on the planet at the time of the Younger Dryas, no humans at the KT boundary. Well, what that quickly, to me, led into was, and I still believe this more than ever, is that there are political implications to the Younger Dryas that there was not with the KT. And I'm not going to digress into all of that. I've commented there on what podcasts that I've done, and I've written things about it. But I think it has to do with, in a nutshell, it has to do with the idea that let's not encourage people to think about catastrophic events in the history of the Earth, because we want people to believe that catastrophes like we are now causing because of soccer moms driving SUVs are causing the catastrophe that's unfolding right now. And I did have a question for Chris, if he's not here, because I wasn't quite clear on, but I think I understood that during marine isotope stage 5E, there were no soccer moms, is that correct? Did I understand that correctly? I apologize for that. Okay, so now what we're going to get into is what it was referred to as the energy paradox. And there was two conferences, one in 1973, one in 1975. And what had happened was the old models were based upon recession rates of the Little Ice Age glaciers, how much ice mass was actually lost during the post-Little Ice Age warming that began in the early 1800s, right? And extrapolating backwards from those rates, it was concluded that, that perhaps the whole melting process for the great ice sheets, as you see right here, maybe took 50,000 years or longer, right? Well, now radiocarbon dating was invented in the early 1950s by Willard Libby, and by the 1970s, a whole database of a whole set of dates had become available that seemed to show that the deglaciation, the onset of glaciation and the deglaciation happened way faster than anybody had imagined, and in a much narrow, constricted time frame, right? So when you assume 50 to 100,000 years, you can, now we can invoke changes in thermal radiation, solar radiation, incident solar radiation onto the atmosphere. And this was based upon changing intensities due to what are called the Milankovitch forces, which are based on precession, obliquity of the ecliptic, and the eccentricity of the Earth's orbit, causes the the changing, slowly changing amounts of heat that can reach the surface of the Earth. So the assumption is that these Milankovitch forces, which are interminably slow, were ultimately the cause for the deglaciation. But now you have this in hand, this data that suggests, well, it happened at least 5 times faster than we had previously imagined. So in 1973, after roughly 20 years of accumulating radiocarbon dates, there was a conference held, and this, okay, before I get to that, just this graphic is good because it shows you the distinction between the Laurentide and the Cordilleran ice sheets. You will note that here in North Carolina, we would not have been under the glaciers, okay? It's possible that some of the higher altitudes above 4,000 feet held small glaciers that do not have, that's controversial. But in any case, the great ice sheets did not reach this far south. Okay, so this was a paper published in the Arctic and Alpine Research in 1973. John T. Andrews was the author of this team that was looking at this. Here's the title of the paper: The Wisconsin Laurentide Ice Sheet, Dispersal Centers, Problems of Rates of Retreat, and Climatic Implications. So what was the problem about the rate of retreat? Well, the problem was that it was happening way too fast, right? So 16 to 20,000 years ago, you had the full ice complex there, and then by 8,000 years ago, it's gone, right? So it's happening way faster than anybody had imagined, okay? So this is John T. Andrews, who led this research, highly respected in the field. And this is the abstract of the paper. Isochrone maps. Now, an isochrone is simply a line that's linking. For example, if you got the ice sheet and it's shrinking, and you go, okay, here's where it was at this time, here's where it was at this time, here's where it was at this time. So now you draw these lines showing how that position or the geometry of the ice sheet is changing with respect to time. So it's a kind of a chronological thing. So a chronozone then is what kind of, or isochrone maps, is kind of what triggered this particular conference that they held. And this is what it says: isochrone maps of the late Wisconsin deglaciation of the Laurentide ice sheet enable estimates to be made of changes in the volume and area of the ice sheet. The average marginal recession between 12,000 and 7,000 BP, which is before present, is estimated as 260 meters per year, and varies, and here was the thing, I've got it underlined, varies little between the northwest and southern margins. Now this made no sense, because you would think, okay, northwest margin, well, that's up on the Arctic Circle in Canada and in Alaska. And the southern margin is in the northern United States. Well, we know that the area of the southern margin is much, much warmer than the area of the northern margin. So wait a second, how is it possible that the ice was disappearing as fast on the northern margin as on the southern margin? That didn't make sense. Okay, that was one of the problems. That was the first problem here. When you talk about problems of rates of retreat, that was one of the problems. Also the dates, because of recalibration of the radiocarbon dating, these dates are now a few thousand years older than they were estimated to be in 1973, so we got to keep that in mind. This paper is, is mainly concerned with the rates of marginal recession of the Laurentide ice sheet, with particular emphasis on the retreat rates experienced during the deglaciation of the northern United States and southern Canada and the Canadian Arctic between 18,000 and 7,000 years ago. Of primary concern is the energy balance at the margin of the ice sheet required to promote the rapid late Wisconsin retreat. The energy balance, because obviously to convert ice to water requires energy, right? The growth and development of the Laurentide ice sheet complex is still an enigma. Unexplained is the growth of the ice cap in its gathering grounds of Baffin Island, Labrador, and Keewatin, where at least today there are low winter accumulation rates. Equally unexplained is the southward penetration of the ice sheet to latitude 40 degrees north or so, where even under full glacial climatic conditions, mass loss at the southern margin must have been considerable. Now, you know that glaciers are not just big chunks of stagnant ice sitting there. you can almost think of glaciers as being alive. They have a zone of accumulation and they have a zone of ablation, where basically think of a slow-moving river, right? Layers of glacial ice are sliding along. If it's a temperate glacier, there's typically water on the bottom of the glacier. You get to if it's starting up at a mountain, in a mountain cirque, it's going to be colder up there. When it gets down valley, it reaches some point where the warmth will be in balance with the growth of the glacier, and then it'll pause, it'll stall at that position. Typically, you'll see meltwater streams and rivers coming out of the snout of the glacier. If the climate warms at the terminus, well, it's going to shrink back. If it's colder, it'll expand. If there's less snowfall up in the zone of accumulation, that will mean it's not being fed as fast. And then if there's more snow falling, it's going to be converted to glacial ice, and it's going to cause an expansion of the glacier. And so a glacier snout would be fluctuating. And that was the thing I mentioned when I started this talk, where I lived and grew up, was right at the margin where that glacier, that ice sheet, was fluctuating. So the landscapes around there were very unique because of that location. Sometimes it would have been outside the glacier, other times it would have been under the glacier. So anyways, think of a glacier ice as basically living. So here's the thing. You know that when you have a lot of snowfall, whoever's grown up in the northern climates, you're going to know you got a lot of snowfall, and then come spring, it melts away, right? And also, studying glaciers, in the spring and summer, there will be glacier melt, and then when winter comes, typically the melting will stop. 3 terms. Subglacial means water under the glacier. Englacial, E-N glacial, is within the glacier. Supraglacial means on top of the glacier. So typically what you'll have is, in the temperate climates, spring will come, summer, and you'll have supraglacial ponding on the top of the glacier, and it will find its way through the glacier, typically to the base of the glacier, and will discharge downstream at the snout. And glaciologists have done dye studies where they'll put a dye in the supraglacial ponding, and it'll be accumulating more and more, and then all of a sudden, like within a day, it'll disappear into a crevice, into a moulin. And maybe anywhere from a week to 3 weeks later, they'll see that water discharging from the snout of the glacier. Okay, so picture in your mind, glaciers are living things. That's one way to think of them. Okay, so where we're at now with it is, let me get that off of there. Okay, so as he's saying here, even under full glacial climatic conditions, mass loss at the southern margin must have been considerable, right? So that's problematic in terms of the growth of the glaciers, because the rate of the growth of the glaciers was paradoxical. It was happening too fast. And then at the end of it, the demise of the glaciers was too fast. At its maximum extent, the Laurentide ice sheet complex was approximately the same size as the present Antarctic ice sheet. In the last few years, the increasing number of radiocarbon-controlled marginal positions led Bryson et al. And Prest to produce isochrone maps on the deglaciation of the Laurentide ice sheet. These maps have been used to estimate the changes in area and volume of the ice sheet as a function of time. The average annual rate of marginal retreat of the Laurentide ice sheet calculated from the reduction in area was 260 meters per year, or 853 feet. This high figure immediately raises the question of what energy sources are available to cause such a rapid retreat. A significant aspect of the Laurentide deglacial history is the high energy inputs required. The paleoclimatological conditions at the southern margin of the Laurentide ice sheet during the late Wisconsin have been discussed by many. A significant aspect of the Laurentide deglacial history is the high energy inputs required to produce the apparent rates of marginal retreat. Okay, so I became aware of these papers and was rereading these papers by the late 70s and early 80s. I was not aware of this at the time this was published. So I wasn't connecting, obviously, this with anything particularly. we'll look at here. The problem imposed by the estimated rapid rates of retreat is illustrated in figure 7, which I'll show you in a second. If the retreating ice sheet maintained a dynamic flow, meaning that it was living, that it was continually adding ice from above to the marginal position, you see, it's not, you can't just assume, okay, 873 feet, whatever it was, the rate of retreat. You're talking about an average that had to have gone continuously through the whole deglaciation phase. Okay, a rate retreat of 200 meters per year thus requires a tremendous vertical mass loss in the vicinity of the ice margin of at least 10 meters and possibly as much as 50 meters or 9 to 45 meters of water. These are minimum estimates of vertical lowering near the margin, as no account is made in them of the forward movement of the ice sheet itself, which in southern latitudes must have been at least 10 meters per year, okay? So this is showing the profiles, looking here, again, this was in the paper, ice marginal profiles illustrating the vertical mass loss required for retreats of 10 to 300 meters per year. Okay, so you've got an 8,000 year span of time during which the ice is retreating, and it has to retreat over 800 feet every year, right? That's phenomenal. Right now, that's assuming that it's a uniform retreat rate. But there's no assumption that we can make or conclusion that that rate of recession was uniform. We now know from the Younger Dryas studies that it likely that disappearance of the ice was interrupted for about 12 or 1,300 years, maybe even reversed, right? So now, if you have reversals or interruptions, you have to deduct that from the total time allotted to get rid of the ice. We'll proceed through a few of these. Yes, going down here we go. If a mass loss of 9 to 45 meters of water is converted into energy required to melt so much ice, then a minimum value of between 72 and 360 kilocalories per square centimeter per year at the southern and northwestern margins. It is necessary to look at these estimates in the light of available energy sources. Net radiation from the sun is the primary energy source over most ice surfaces that leads to ice melt, although with an increase in maritime influences, convection and condensation increase in importance. So net radiation is a complex heat source. It is the net product of incoming global and long-wave radiation and the outgoing long-wave radiation, and consequently is not an easy parameter to model. In the area of the former southern margins of the Laurentide ice sheet, 12,000 years before present, the present annual net radiation amounts to 40 kilocalories per square centimeter per year. Got it? 40. Now, back up. And there was possibly as many as 360 kilocalories per square centimeter per year to affect this rate of retreat. So 40 into 360 gives you what? It's definitely not enough energy, right? And this is at the southern margin. This is not up by the Arctic. Compared to between 5 and 10 kilocalories per year along the former northern margin today. These values have to be adjusted for the amount of net radiation falling during the summer months on an ice surface with an albedo of approximately 0.5 for an effective computation of this energy source ablation. So we'll just skip over some of this for the interest of time. So the conclusion of this 1973 conference was they didn't have an answer for this. How is it that the ice melted away? How do you provide energy that's 4 or 5 times the amount of energy available at the southern margin, and that's even at the northern margin? Well, this is why it became known as the energy paradox. So a couple of years later, they come back to it. Now they've got more data in hand, and the problem has become even more confounding. So they held another conference. This one was led by Kenneth Hare. He wrote the paper on it in 1976 in Quaternary Research, Late Pleistocene and Holocene Climate, Some Persistent Problems. Okay, so we'll just look at this quickly. He goes, We'll go down to the last sentence here. All I can do in this situation is to point out some disturbing and persistent problems that tend to defy solution. Well, that was the energy paradox right there. The energy requirements of glacial retreat, a problem clearly set out by Andrews. So we're going through this because I want you to see that this problem was actually defined years ago and never solved. Even the most conservative estimates exceed the rates of energy delivery that exist today in those areas. Calculations for the Scandinavian ice reveal a similar paradox. From where was the energy derived to bring about so rapid a wasting of the ice sheet? Well, in my mind, look at this, I didn't know the answer, but I'm thinking, well, it must be two things, because I'm thinking about this, pondering this, and it's getting into the late 70s, into the early 80s, and I'm thinking, well, it's either got to be the sun or it's got to be some kind of an impact. An impact because with the publication of the data that was now coming out in the early 80s and the discovery of a lot of impact craters and astrobleams and so on, there were energy calculations that showed that an impact could release tremendous amounts of energy. Mark, this morning, he showed that the Tunguska event was roughly equivalent to up to a 15 megaton explosion, which is basically, and he showed you the graph, right? Remember the graph he showed juxtaposed on Asheville to show you the area of total devastation? Over 800 square miles, 2,000 square kilometers of old-growth taiga forest were utterly and completely decimated. 200 square miles right under the epicenter of the aerial blast were incinerated to nothing, right? It's releasing an enormous amount of heat. Now, let's come back to the scenario that seems to be evolving in terms of the Younger Dryas, is that possibly we're looking at a multi-impact event, a decaying comet that could have actually created a storm of Tunguska-like objects, and it would seem like such a phenomena could perhaps fill the bill. I don't exclude the role of the sun, and there's actually reasons why I don't. I think because we have to begin to look at the solar system as an integrating system, and that we now know from satellite surveys of the sun that the sun does seem to be affected by the infalling of cometary masses. The whole Kreutz family of sun grazers, they're called, seems to show that, and there's a lot of work that still needs to be done on this, but seem to show that there's a connection between solar storms, coronal mass ejections, and the infall of the sun-grazing comets. Now, if that turns out to be true, and we're looking at a multi-impact event, possibly not just, it also came up the question, somebody asked about, what about the end of the Younger Dryas? And Mark pointed out that there was some evidence that the Younger Dryas, the end of it, there might have been an impact event there as well. And there was also, I don't know if he mentioned, but there was Meltwater Pulse 1A, which was the biggest of the meltwater pulses, and I'll show you a slide coming up in a second, and that's dated at about 14,500 or 14,600 years ago. So finally, he says here, this is Kenneth Hare writing, Andrews calculated that the average rate of marginal retreat of the Laurentide ice was 260 meters per year over the whole retreat phase. Now that's average. That doesn't mean that every year it was 800. If some years it didn't retreat at all, that meant that other years it retreated a lot more than that, right? To estimate the marginal value of the vertical wasting, we'll jump down here to the bottom. The lower of these figures corresponds to net radiation values typical of subtropical areas. The higher figure is 3 times as high as the highest known contemporary regional net radiation over tropical oceans. So get that. If that higher number is actually the value, it means this. The implication is this. If you take that entire ice sheet complex, put it to the tropical oceans, it's still going to take, it happens 3 times too fast. So what's the explanation? Well, there has to be some kind of input of energy from outside known terrestrial sources, or at least known solar sources if it's external to the terrestrial system. Could volcanoes have done that? Not adequate. What else could have done it? Well, this is where we come back, and this is, with this kind of information and this turning over in my mind, this is where I was thinking, well, you know, when I started seeing the evidence that perhaps Earth gets struck by things from space a little bit more frequently than anybody had imagined, it seemed to me like, well, in some scenario, maybe this provides the solution to the energy paradox. Anybody who wants the basic calculations, here it is. And you've seen this because Mark has shown this, the amazing Younger Dryas and what happened there. This spike that I'm showing right here is the 14,500 meltwater pulse 1A. And then this trough here is the Younger Dryas. And then this warming spike here is that he said happened in less than a decade. Some studies suggest it even happened in less than 5 years. Was the end of the Younger Dryas at about 11,000, between 11,005 and 11,600 years ago. That number's always been interesting to me because remember, going back to mentioning how I was reading about Atlantis, and then I learned from reading Plato's dialogues and the commentaries on Atlantis that he dated that at 9,000 years prior to Solon's exile in Egypt, which is well dated at 600 BC. So Plato, and I would recommend reading those two dialogues and that's our primary source for Atlantis. There's been so much speculation and fringe and pseudo speculation around the Atlantis that it's really almost become contaminated, and you're not even allowed to say the A word. But if you read the two dialogues, Timaeus and Critias, what you're going to find in there is what he's actually saying isn't as outlandish as it's often made out to be. But he gives this date of that supposedly the elder priests are telling Solon this. They're saying that there was this tremendous catastrophe 6,000 years ago. There was a great mass wasting event on the Greek peninsula. Most people overlook that, but he specifically refers to that in the reference, and a great seismic event, an earthquake that caused the island of Atlantis to sink. Now, I've given, like somebody said, I did a 10-hour lecture. Not all at once, by the way. 2 parts. Actually, because I wanted to set the record straight and show, look, let's strip this Atlantis thing of all the pseudo stuff that's been attached to it, and let's just look at what Plato actually says. And what might have concluded from that is, well, he's describing an advanced maritime culture, maybe along the lines of the Phoenicians or the Minoans, but more elaborate, that had found refuge perhaps on an island complex. And I showed the meaning of eustatic sea level rise and fall based upon glacier expansion and contraction, what Chris was referring to as transgression, which is sea level rise, regression, which is sea level fall, and that there was actually very likely, there was evidence that there had been seismic events along the mid-Atlantic ridge that were based on isostatic adjustment of the Earth's the globe of the Earth, the sphere of the Earth, as a result of this mass shifting of glacial mass from the continents into the oceans. We know that from isostatic rebound, which is the vertical movement of the Earth's crust, that in the region of the central Laurentide ice sheet, there may have been as much as a 1,500 feet rebound after release of the glacier mass. Most of the Laurentide ice sheet drained into the northern Atlantic. Some of it drained, a lot of it drained into the Arctic Ocean, which ended up in the North Atlantic, and you had a 400-foot rise in sea level. Well, just as there was an isostatic adjustment in the North American craton with the release of the ice, it's not overly speculative to think that there may have been an isostatic adjustment along the mid-Atlantic ridge, which was some of the thinnest continental oceanic crust on Earth, right? And so I went into great detail on that, and I actually accumulated a whole lot of empirical data showing that there was all kinds of evidence that large regions along the mid-Atlantic ridge had been much shallower during the late Ice Age. not only because of the eustatic changing in sea level, but also isostatic adjustment of the ocean floor. I also showed the position of the Gulf Stream during the late glacial maximum, which made a 180 just north of the Azores Plateau. So I've since then accumulated a lot of information on the seafaring capabilities of ancient humans, and it's actually going back now 35 to 60,000 years. Apparently humans, like evidence shows that people were able to sail from the Eurasian, the southeastern Asian landmass to Australia as long ago as 60,000 years. I think it was one of the speakers, maybe it was Mark or Chris, I think it was Mark, saying that, you know, no, it was Luke, saying that, talking about that oceanic current that would carry you west. Well, it would carry, if a ship went astray outside the Straits of Gibraltar, got caught in that current, it would be delivered directly towards the Azores. And actually, with the inversion of the Gulf Stream at that time, that probably would have been a good place for anything that could be construed as a culture to form during the Ice Age. Now, I'm about to get into something here and show you that why I think we need to be open-minded and willing to rethink what may have gone down in prehistory times, meaning going back to what we now define as the Holocene, because all of what modern we think of as history has happened during the Holocene, and everything beyond the Holocene is now prehistoric. And we have assumptions about what went on, but two things. One, if archaeologists are looking at those times, late Wisconsin in terms of the North American ice sheet times, and they're looking for a reflection of our own society, you might not see it. Because the question we have to ask is it possible for a culture to achieve levels of advancement that doesn't look anything like our own modern fossil fuel-based culture that we've developed post-industrial revolution? And I think the answer is, well, we should be open-minded to that. So anyways, let's go here. You don't need to see this. Here's where Richard Fairbanks is first showing that there were, let's see here, that there were two huge meltwater spikes. The sea level was 121 plus or minus 5 meters below present level during the last glacial maximum. The deglacial sea level rise was not monotonic, rather it was marked by two intervals of rapid rise, which has come to be known as Meltwater Pulse 1A and Meltwater Pulse 1B, which are shown in this graph right here. And you see that Meltwater Pulse 1A was the larger of the two. This one dates roughly at 14,005. Meltwater Pulse 1B right at 11,600, which I just pointed out happens to be coincidentally the same date that Plato defines as being the subsidence of Atlantis. Coincidence? Maybe. But if we're open-minded, we would think, well, maybe not. Let's look at this further. That's what I did. And I'm not going to get into that today because you can go find 10 hours of me ranting on about that. Because I wanted to make the case solidly. So I really took a deep dive into the geophysics, the marine geology, the oceanography, and all of that to show that it maybe isn't quite as implausible as some people may think. Anyways, I think we may want to add a third spike in here now that, like Mark was showing, there might be a third spike that coincides with the Younger Dryas melting. This goes back, I think this was in the 1980s, when this graph was first shown here. And the dashed line represents the insulation curve. This would have been consistent with Milankovitch forces, but you can see that the curve of actual sea level rise doesn't look anything like the Milankovitch rates. We're not going to spend a lot of time. Just showing this briefly. I'm not going to get into that at all today, but this is mortality graph. Each one of these blocks, each one of these squares represents a particular fossil specimen of an extinct megafaunal animal. And you can see right at the end, if you look at the bottom there, you'll see between 11 and 13,000 years ago, there's a major spike in megamammal, megafauna mortality. And that seems to coincide very nicely with this graph and with this graph right here. We'll have to skip some stuff, and I'm just going to show you some of this. You can now start getting an idea of the geomorphic consequences of these rapid meltings. So let's take a look at this very quickly. Here we have western United States. This is the Columbia Basalt Plateau, which is a series of basalt floods that occurred between 6 and 17 million years ago. The source of those, this is interesting, you can look at this. You can see this jumbled area right here is where you have the feeder dikes that fed the basalt outflows, but you can trace over the 17 million years the pathway of the northwestern plate here, that if you follow the route back, it's the southern plain of Idaho, now occupied by the Snake River, and it leads us right back to the mantle plume that's now under Yellowstone. So Yellowstone is a remnant of the basalt floods that created the Columbia Basalt Plateau that you see right here. Here's another version of it. This is a very nice, and one reason I focus on this is because the megaflood features are more spectacularly represented here than just about anywhere else on Earth. Although in the Altai Mountain region now, we found out with the thawing of the Cold War in the early 90s that there is a region there that has very similar scale features. And I don't know the explanation. I haven't studied into it to that extent yet to have an opinion on it. I'm very curious if there would be a correlation between this and the flooding of the Altai Mountains. But what you see here is, this is a basalt plateau, and there's a few things just to call your attention to. The ice encroached. This is the Spokane River here. The Columbia River is coming out of British Columbia here, cuts to the west, comes up here, meets the Okanagan River. Together they flow down through here along the margin between the basalt of the plateau, and so you've got basalt bedrock here, and then immediately to the west you've got granitic bedrock. So the Columbia has carved a deep canyon between the basalt and the granite, right? So if you're right in this area, if you're on the east side, you're going to have basalt bedrock, and you cross over to the west side, you're going to have granite bedrock. And of course what that is that the pre-basalt flood Columbia, once those basalts were spread out here, it diverted the Columbia around, and there's subterranean evidence that originally the Columbia flowed right down across through what's called Wallula Gap right here. Now, during the melting, during the floods, you had major floods coming down this route, which is the Columbia. You had a feature here called Moses Coulee, which is a gigantic spillway. You have Grand Coulee here, and then you had over here, you had what is called the Telford Scabland Tract, then you had what is called the Cheney-Palouse Scabland Tract. Grand Coulee, it's estimated, was conveying over 300 million cubic feet per second. Now, to try to put that into some scale, we can say this, that 300 million cubic feet per second is about the same volume of flow you would have if you took every single river on Earth, think of every continent, think of the great rivers, the Mississippi, the Columbia, the Hudson in North America, the Mackenzie, the Yukon, go to South America, the Orinoco, the Amazon, go to Eurasia and think about the great rivers there, and think about the Mekong River and the Yellow River of China and the Thames River. Go to Africa and think about the Nile. Think about all of these tremendously great rivers. Now take every river on Earth, combine that flow, it's still only going to be 1/10 of the flow that created Grand Coulee. So, and this is, yeah, okay.
Just to say, we got 10 minutes until dinner, and we're going to pause.
Yeah.
Get some food, and then we're going to come back for your second half.
Sounds good.
Okay.
So I got 5 more minutes to go?
10 more minutes, and then
Okay.
we're going to eat, and then we're going to refresh.
That's what I had in my mind, was somewhere I knew. My instincts were telling me. All right, so here is the man, J. Harlan Bretz, one of my heroes right here. Here he is in, who? Now you're making me feel all conspicuous. All right. And oh, by the way, J, just simply the letter J is his first name. So if you see it written out, J. Harlan Bretz, and there's a period after the J, they don't know anything. All right, so here's just a quick map showing the lake basin, the ice dam, and then the outflow areas. This is the channel scablands that you see here. Over here is the Columbia, Moses Coulee, Grand Coulee is here, Telford Scabland Tract is in here, Cheney Palouse is in here. All of this water flow all converged on the southeastern quadrant of the basalt plateau and flowed through Alula Gap. Now, September, we're going to be going our second or third excursion, going in exploring this area of western Montana, where the lake basin, I'll say lake basin in quotes, okay? Because as you'll come to find out, I don't think it was a lake at all. It was a huge volume of water, temporarily stored there, maybe several times, but I don't think it was a lake in the sense that we think of a lake. You think of a lake, you think of a nice placid surface, frogs croaking on the shores, fish swimming in the water, Okay, so here we go. Now this one, see the Cordilleran ice sheet. You're going to find out why I'm suggesting renaming these floods from the Missoula floods to the Cordilleran floods, because I don't believe at this point that glacial Lake Missoula was the ultimate source for the water. And we'll get into that in the second half. But what you have here is essentially not going to be correct. Why? Because they're showing, the blue is showing, well, it's showing the scabland tracts. And in fact, there was so much water that it completely inundated Willamette Valley 400 feet deep, right? Now, you see this blue area here. If that represents the water flowing over the scablands, that means that the lake is already drained, right? So this is not really accurate if the implication is that the lake is full pool here, which is what it's showing, and the channel scablands is completely submerged. And here's a more detailed close-up map of glacial Lake Missoula, and what you can see here is how intricate the lake basin is. And this is going to have a big influence on rates of drainage, right? Because if you go here to the Bitterroot Valley, right here, you can release the water up here at the ice dam, and you're going to have a very rapid catastrophic outflow. But by the time you get to these distal reservoirs here, the energy levels are going to be very low. In fact, there's some new computer studies I have not included in this presentation that do in fact calculate the velocities of the discharge from these various reservoirs. And you got to bear in mind that if you take water that's in the Bitterroot Valley, for it to discharge out here, look at this tortuous route that it has to go. It goes through a series of constrictions and openings into basins. It makes hairpin turns. All of that is going to cause energy losses, and you're going to have this hydraulic head up here that's 2,000 feet of water, because we've tracked that 4,200 foot strand line. The floor of the valley here is just over 2,000 feet, so the implication is that the water was over 2,100 feet deep, which, as I pointed out, creates a basal pressure on the heel of the ice dam of in excess of 950 psi. For reasons that will become apparent to you in part 2, I don't think glacial ice is up to that level of stability that it can hold water in at those kind of pressures. Okay, so let's just keep moving here. This was an important paper that came out in 1973. Victor Baker was the author of this. This kind of marks a transition in the thinking, because Victor Baker brought some more sophisticated hydrological science to the study. He looked at a place called Rathdrum Prairie, which is this area right here. You can see, for those of you that, I know some of you are here from Spokane, Rathdrum Prairie is right here. The ice dam would have been where Lake Pend Oreille now is, and the interesting question is, where was the terminus of that glacial lobe that would have provided the hypothetical ice dam? But when you consider the flows that came through here, if there was terminal moraine, it would have been completely flushed away. Now this is the mouth of the Clark Fork right here, where Pardee did his work, and Baker did his work right here in this area called Rathdrum. So let's go back here. Now here's what he concluded. Maximum discharges through scabland channels range from 752 times 10 to the 6th cubic feet per second into Rathdrum Prairie. Okay, so 752 times 10 to the 6th cubic feet per second is almost double what Pardee calculated for Eddy Narrows in the Clark Fork Valley, almost double. So was Pardee that far off? Well, no, he used a fairly well-established engineering calculation used by hydraulic engineers called the Chesi formula, which may be not as accurate as the more sophisticated formulas that Baker used, but it's not off, it's not double. It might be a few percent one way or another, but it's not going to be double. So right there to me is a major hint that's been overlooked. How come Baker's estimate is almost double the estimate that Pardee came up with? If I go back to here, remember, Pardee's, the total water creating the Missoula floods is coming out of this valley right here. So this is 9.5 cubic miles. This is over 17, almost 18 cubic miles per hour passing through Rathdrum. So how do you explain that discrepancy? Well, in part 2, I'll show you. This is an area, a satellite photograph of the two great scabland tracts, Telford over here, Cheney Palouse here, and you can see that what you've got is the dark basalt underneath covered by lucial topsoil, anywhere from a few dozen up to 200 feet thick, and when the floodwaters gushed over the basalt plateau, they washed away the loess and exposed the basalt underneath. And you can see what are called here, the term is anastomosing stream channels, that's branching where they part and they come back together. And that's what you have here. Here's the word that you can add to your vocabulary, anastomosing. So you can use that to impress your friends. And here's an aerial of the Cheney Palouse, and you see these island-like features. This is Mars over here, where very similar floods took place, and yet the geomorphological features are very similar. The term here for these is streamlined erosional residuals. You've got streamlined erosional residuals here in the Cheney Palouse scabland. You've got streamlined erosional residuals here on Crais Planitia on Mars, because we now know that Mars, long time ago, had really big floods, which is a whole nother interesting question in itself. Here's a very close-up where you can see. Now, initially, picture this. The flood comes over the land as a sheet, but it quickly will exploit any low-lying area or any zone of weakness, and it will start to become concentrated in that zone. Well, once that does, the water is getting concentrated in this zone, accelerates its erosion, and eventually it will get deep enough and wide enough that it will capture all the water flowing over the surface, right? So what you got here, you can see, is the latter stages of the flood. These would have been islands. So you would have been essentially surrounded by a gigantic raging river that would have been between 100 and 200 feet deep. And right in here, roughly 10 miles wide. And I'll show you this very quick, and then we'll break for dinner. You all have seen, how many of you have been to Niagara Falls? Quite a few of you have seen the Great Horseshoe Cataract at Niagara. And there's a reason. It has simply to do with hydrology, and we're not going to get into that, but it's water flows faster in the middle of a current typically, all things being equal. And so wherever the water is flowing faster, the erosional rate is faster as well, right? So essentially what you've got with these cataract formations is the inverse of the velocity profile of flowing water. So here's, like it shows here, 800 feet across, and then here's one of the great extinct cataracts of the channel scablands with Horseshoe Falls superimposed for scale. Here's an aerial view that I took in 1998, and up here in the corner is Horseshoe Falls, and we're only seeing one small part. This is one alcove. There's a whole other alcove here. The whole complex is over 5 miles wide. It's 400 feet from the upper rim of the cataract to the floor. Down here we see the remnants of plunge pools that were carved out by the enormous erosive potential of the water pouring over. At the time this water came down, flowing across this particular area right here, it was 400 feet deep. So the water was as deep as the cliff is high, and during the peak of the flood, you wouldn't have even seen a waterfall. You'd have simply seen a bump in the water flow. This right here is a 1 to 24,000 inch, 1 to 24,000 scale, 7.5 minute topographical quadrangle showing one of the great cataract complexes that we visit on our field trips called Potholes Cataract. And it was the first topographical map of this particular feature that J. Harlan Brett's got his hands on in 1910. And he's looking at this feature and he's going, what the hell am I looking at? And that's what set him off on his quest to try to understand these floods. If we look here, we're going to see that there's these round lakes. Those round lakes are formed by extreme turbulence. There's a process that has been identified using, and it's named with an Icelandic term called kolking. And kolking is a whirlpool that's formed in very deep, turbulent, fast-moving waters. You can literally think of it as an underwater tornado. It has tremendous upward sucking pressure. At the same time, it can drill into bedrock. It will pick up debris that it'll train into this spin that will accelerate the drilling into the bedrock. Pothole formation is one of the diagnostics that you use, or that we would use for indications of larger or mega flood scale events. So in the middle here, we actually had two alcoves in this feature. You see the Finger Lakes here, where the water I just described how it becomes channelized. So we see first it becomes channelized, then it starts pouring over this ridge right here and eating its way back, and these cataracts are recessional. As the water's pouring over, it's eating the cliff face backwards, upstream, and so that's called a recessional cataract. The rock between them is called the rock blade, so we're going to leave that. The rock blade, got it? So we'll continue a little bit later, do maybe another hour's worth, and get into the good stuff. Oh, thank you.
Okay, guys, get some air, get some drink. The bars are now open. The way that dinner was going to work is there's a dude with a beard who's going to come around, tap your table so that we don't have to stand in a queue. You are already in a queue. If you don't have a seat, find one at a table, and we're going to get across much quicker if we do it with the dude with the beard. There he is. He's waving over there. He's going to come and he's going to tap your tables.
Yeah. The dude with the beard, that's, by the way, that's not me.
Okay. One other important announcement for the live stream audience. I've just talked to HowTube, and we have an unplanned agreement to extend it another hour, well, not another hour, to take an hour break, come back after we eat here, and if you're watching it by live stream, come back at 8 o'clock, and we'll try to have it back up for whatever Randall's willing to give us. Might even have some music, who the hell knows. But live streamers, hang in there. We're breaking for an hour, and stick with us. And RandallCarlson.com is online.
Also, Bradley reminded me that we're going to be doing an Asteroid Day live stream, and we're going to try to cover some stuff that didn't get covered here. I mean, there's going to be a lot of great stuff covered here, but we're kind of orienting it a little bit to come up with some stuff that's not being covered here, but will overlap. And of course, Asteroid Day is June 30th, and June 30th will be the 115th year since the Great Tunguska event of 1908. So we're going to get into that and similar things, that some of what you saw today, particularly with Mark's presentation, but we'll get into a lot of things that will supplement with what Mark presented, and just, it's going to be some cool stuff. Now, I did neglect earlier, I usually like to do this when I am doing a presentation to a group, is what I'd like to do is we'll just go around the room, and if everybody could just stand up, tell your name, where you came from, and what your preferred pronouns are, and then we'll get started, okay? No. Oh, I guess George says we don't have time for that, so sorry. Okay, it looks like we're right where we left off, so let's just keep going here. Okay, so I hope you learn a little bit of vocabulary out of this. Now, these are recessional cataracts. You know what that is? That's a cataract because the cataract is being eroded upstream. And here we have, in a complex like this, we have what are called the alcoves. There's two of them. They're separated by a rock blade, it's called, which is this sharp thing that's coming out here like this. And then this is Potholes Cataract, and this is Frenchman Cataract. It's all part of the same overflow of Babcock Ridge. It's called out of Quincy Basin. We're not going to get into a whole lot of detail on the specifics of the Scablands flood. We do that prior to tours. When we do tours to these places, we'll always have several Zoom meetings to get people up to speed on what the purpose is, where we're going, some of the nomenclature, some of the basic concepts and principles, and the things that we're going to be learning, okay? So you'll see here, this one also has a rock blade. And now we're going to get into just looking at some of the power of this moving water. And these are erratic boulders that were not moved by glaciers because they're outside the glacial margin. And you can see this is a pretty good sized rock. And this is on the hills flanking the Columbia. I'm just going to show you briefly some examples. This is the Chelan Butte erratic, has Bradley sitting on top of it. And this is on a ridge. It's about 400 feet above the modern Columbia River. And what's interesting, this is the west side of the Columbia. Just before the break, I mentioned that on the east side of the Columbia there, in that north-south reach of the Columbia, is the basalt of the Columbia Basalt Plateau, and on the left side is the granite. Well, here is granite bedrock underneath this landscape here, but the erratic is sitting 400 feet above the Columbia, and it did not originate there. It originated on the east side of the Columbia River and was somehow transported over here, deposited on this ridge 400 feet above the modern Columbia. Here's another one, the Wenatchee erratic. You can see the black basalt here. This also is about 400 feet. What I'm guessing here is that the water actually rose up over 600-700 feet deep along this reach of the Columbia. In this water flow, this is a great little illustration I found in an old 19th century geology text, believe it or not, and it's basically showing the mechanism by which a lot of these erratic boulders were transported via iceberg transport. So what you have to picture now is when you start getting the image of these tremendous floods, you've got to imagine roiling, boiling, turbulent water, and it's going to be choked with gigantic icebergs because one of the things that we know that, for example, that there are erratic boulders that are transported by glaciers, but now there's erratic boulders that are iceberg transported. And what happens is you got to try to imagine in your imagination how you get gigantic icebergs, some of them that by implication almost have to be the size of tanker ships, and on these icebergs are these huge boulders that can weigh thousands of tons. How does that happen? Okay, so whatever this mechanism is that's triggering these floods has to take account for that. This is going to show you, these are typical current ripples. It says here, this is the floodplain. This is near where I live. I go walking down just beyond the expedition. There is a creek channel. And in the time that I've been living in this area, which is over 30 years now, only the creek has only swelled up and spread onto the ancient floodplain twice. Now this was during Hurricane Ivan when it came through. So you can see here there's current ripples, and here you see I've got the measuring tape. By looking at the trees and some nearby buildings, I could find the high water mark, and it was right at 24 inches above the surface of the floodplain. So that gave us an indication of the maximum depth of the water. So these current ripples here, They're scaled to that size of water. Now that flow is probably between 5 and 8 miles an hour at the time, so it's not moving anywhere near the velocity of some of the flood currents of the Missoula floods. Here you're looking, if you look carefully, you'll see that the wavelength is roughly 3 inches, amplitude is about 3/4 of an inch, right? So then we get to this. This is looking north in Camas Prairie, and what you're seeing is a gigantic current ripple field. Up here, you find a gigantic fan delta. The floor of this is at about 2,800 feet above sea level. The water level hit 4,200 feet. So the width of this valley is 5 miles wide. So what you have to picture is a river, temporary river, 5 miles wide and 1,400 feet deep. The velocity of that flood water is probably 40 to 50 miles an hour. And this is some extraordinary current ripples here. I can't spend any time on this because I've got way too much already to show you, but Bradley and I have covered this territory. We've gone to gravel pits where we can see cross sections of the current ripples. Lot of interesting information extracted from this. But the point is here is this is something that we will visit in our Montana tour. This is one of my favorite places, and there's you can see the highway right here. And the highway comes through, these range of hills is the Marco Hills, and Marco Pass is right up here. We usually come from the south. We try to come later in the afternoon so that the sun angle is low. And when you come around this, there's a curve right up here. There's a pass between the hills. You come around this curve, and there's a pull-off right there, and you can see the whole spectacular 10-mile-long Camas Prairie Basin stretched out before you, and you can see the rolling current ripples, and it is a spectacular thing to see. And then, like I said, the ones here at the upper end, they're as tall as a 5-story building. So there are farms that are down in the troughs, and if you are in that trough, you're not going to see over because it's, the hills are high above you. And it was this that J.T. Pardee saw that led him to write that paper called Unusual Currents. And yes, indeed, when you have a ripple field like this, the currents could be correctly and accurately categorized as unusual. So here's your map of the general area. The Camas Prairie that we were just looking at is this feature right down here. The water came from the north. This is Flathead Lake. Here is the Mission Basin right here. This was the biggest reservoir of Lake Missoula. And here's Clark Fork Valley and the outlet. Here's your arrow indicating current direction flow. The idea is within the standard, I call the standard model, there was an ice lobe that came down out of this valley up here. It's called the Purcell Trench. That ice lobe came down, filled what is the valley now occupied by Lake Pend Oreille, which, by the way, right in here is 1,100 feet deep, 1,100 feet deep. In fact, it's so deep that the Navy field tests 3/4-inch scale model Trident submarines in this lake right here. One of the great outlets was through here, and that when I showed you earlier where Vic Baker did his calculations, which was Rathdrum Prairie, that's right down here. Now, the standard model is that there was this lobe of ice that came down through the Purcell Trench, passed through what is now occupied by the basin of Lake Pend Oreille, came down here and terminated somewhere between Rathdrum and Spokane. And, but again, like I commented before, that exact position is very hard to discern because when you figure 752 million cubic feet per second rushing through here, whatever terminal moraine is going to be left there, going to be left in the wake of the glaciers, is going to be completely washed away. So that's one of the things that makes it difficult to determine where the terminus of this ice dam was. However, it had to be at least a half a mile thick in the region of the ice dam. Now, that's a Cabinet Gorge Dam that's there. That's when we go do our Montana tours, oftentimes we'll begin either in Spokane or Sandpoint, and then we'll head east, usually going up the Clark Fork River. We'll hit the spot where the Cabinet Gorge Dam is, because that is pretty much right where the hypothetical ice dam was, where the ice met the water. Now, our first trip up in 1998, I went and sought out Roy Breckenridge, who had done most of the field work in the area of the ice dam, because we were going there. We hadn't actually gone there yet. we were going there, and I wanted to know, Dr. Breckenridge, where exactly will we find that position where the ice and the water met? And we had a conversation for maybe 45 minutes, and at the end of it, he kind of almost confessed. He says, I don't really know about this ice dam business. And I thought, you know what, that's what I was waiting to hear, because I don't either. I'm questioning the efficacy of glacial ice, because earlier I had talked to a geologist out of Calgary, Canada named C. Warren Hunt, who is an engineering geologist and a consultant to governments and companies and things that were going to build dams. And he was the one who would come in to examine the geological substrate to determine whether it was suitable to withstand the kind of pressures that would be placed against the bottom of the ice dam by the reservoir. Well, he was looking at claims in Canada that there was what he called Glacial Lake Calgary that was 1,200 feet deep and was supposedly held in by an ice dam. And he went and studied it and wrote a couple of papers that were published in the Canadian Bulletin of Petroleum Geology. I'm sure most of you have read those papers. Anyhow, I read his papers, and I contacted him before we went on our first trip. His papers were written in the 70s. This was 20 years later. He was quite old by the time I talked to him. And I asked him, you said in your papers that the idea of a glacial dam holding in 1,200 foot deep Lake Calgary made no sense. Do you still hold to that? And he says, oh, absolutely. And then in his second paper, he addressed the question of Lake Missoula. And he said, all of my criticisms of Lake Calgary are double for Lake Missoula. He says it's just purely frivolous to assume that you're going to have glacial ice holding in water, glacial ice where, what's the tallest dam in North America? It's Hoover Dam. It's just over 700 feet high. This was the tallest dam we were able to build in North America with bedrock grouting, steel reinforcement, all of that. Over 700 feet high, it wouldn't be suitable to withstand those kinds of pressures, which would be only a third the basal pressure on the ice dam in the region of Lake Pend Oreille. So he was adamant that the whole scenario was a total impossibility. Okay, so then we kind of were motivated by that idea and searching, well, if the ice dam is implausible, like he maintained, and does that mean there was no glacial lake there? Well, it depends on how you define a glacial lake. The question is, and I'm going to get to a quote here in a minute by geologist David Alt, who points out the inconsistencies between the body of water that was occupying the valleys of western Montana and an actual lake, which led us to believe that maybe we're not looking at an actual lake. Because here was the scenario. What they did was they assumed that the flood came through, burst the ice dam, the lake drained pretty much completely, the ice advanced, sealed off the valley again, and then the water rose behind the ice dam. And it did this, like I mentioned earlier, based on the studies of the rhythmites, it might have done this 30 or 40 times. Then Brian Atwater went up to the Sanpoil River, which Bradley and I have visited several times, and by varve counting concluded that there was maybe as many as 90 separate floods, which I assume was the implication was 90 separate ice dams. Now, the way the models have generally worked is that they assume that the Clark Fork River, which is the river flowing northwest through this valley, they doubled the discharge of that river, roughly, and then assumed that it would take 50 to 100 years to accumulate the 600 cubic miles of water that was full pool for Lake Missoula. So in the interim there, you would have two things happening. You would have the ice dam advancing through this, from the north, through the lake basin, and never have I seen the question addressed of at what point the lake basin appeared there, because if the lake basin was already there, that means that the ice had to fill that basin 1,100 feet deep before you've even reached the ground level. You see what I'm saying? So that raises to me some really thorny issues about the whole scenario. Well, anyways, the water, because ice is what, 93% as dense as water. This is why ice floats. Well, what this means in effect is if the water is 2,100 feet deep, the ice has to be at least a half a mile thick right there. Now, typically in glaciers, you'll have a marginal profile, it'll taper down, and it'll maybe be a few hundred feet up to perhaps 1,000 feet maximum thickness near the glacier margin. So how far south does the glacier have to advance before you've got a half a mile of ice right here blocking the Clark Fork? And supposedly then a tongue of ice went upstream, which was actually to the southeast, and right there near the Cabinet Gorge Reservoir, which is one of the stops we typically make on our Montana tours. So you can see here's where the ice supposedly met the water, which I think did in fact happen. But I'll circle back to that in a minute. Okay, so let's proceed on. So here's a closer up look of that same region. The Cabinet Gorge Dam is right in here. You can see it's right by the Idaho-Montana line. I've got an arrow pointing to a prominence sticking off of a tributary valley here. Now, right here at this area, the valley floor is about 2,100 feet above sea level. The high water mark is still at 4,200, so you're looking at 2,100 foot depth of water, okay? Now, think about this. I didn't have let me see if I've got my calculator here, because we're talking over 950 pounds per square inch, right? Per square inch. Well, there's 144 square inches in a square foot, so I'm gonna multiply 144, what did I say? There was 950, that's roughly, within 10 roughly. So 950 times 144, that's 136,800 pounds per square foot. So I'm thinking, okay, I looked up what is an example of something that weighs roughly that much, that would have that weight per square foot. One of the things that was actually very close to that was a Sherman tank. So, okay, so what, if you think about it, if you've got an ice cube, 1 cubic foot, and you put a Sherman tank on top of it, would that ice cube exist after? So that kind of tries to give you an idea of the pressures. Okay, so now we're going to zoom in on this particular prominence right here. And you can see this prominence kind of sticks off. It's actually called a valley train. This would have been a tributary valley. So the waters that were over 2,000 feet deep would have backed up this valley a long ways. And we haven't gone up and found the high water mark in this particular valley, but we have in others where you can actually see where the backrush of water went up the tributary valleys, sloshing up and drops a layer of gravel and then turns around and drains back out. So that's one way that you can identify, that's a diagnostic for finding the high water marks. But now let me go to, watch this, Google Maps, and right here is a gravel pit. And here you get a closer view of that gravel pit. We've been to this gravel pit multiple times. Here's a photograph taken in 1998. And this is the Drive Creek gravel pit. Now this picture is taken facing southwest. Now what you can see here, which is really a cool thing, is that when you have these gravel sand deposits that are laid down by these catastrophic floods, it almost creates like a photographic cross-section of the flows, because you have to picture these water flows now are choked with sediment. They're rapid, they're moving swiftly, they're grinding up the land, they're eroding and plucking and breaking up rocks, and so the water is really almost more like a thin slurry rather than water, right? When this stuff washes in, it constantly lays down stuff, right? And builds these layers like you see here. Now these layers are called foresets, and then what you have is a bedding sequence here of foresets. Foresets are a paleocurrent indicator. What do I mean by that term? Well, it's something that you can use to determine which direction the water is flowing that created it. The down current direction, your deposits, your foresets as they're called, always dip or tilt down in the direction of the current flow. Okay? Got that? So by looking at a cross-section like this, you can determine, okay, so knowing that now, when you look at this, was the flow from right to left or left to right? Right to left, yes. So you're already budding geologists. And if you choose to go on a tour with us, what I'm trying to do on these tours is there's a whole language that goes along with this. It's got its own grammar, its own syntax, and it's a language that people can learn, and I'm trying to teach people to read it. I'm still learning it myself, but I've made quite a bit of headway into it, and I'm trying to teach other people to look at these features and be able to diagnose what happened. It's very much like forensic geology, like Scott Wolter does. And what Mark showed us today, just like when you're trying to analyze a crime scene, you go in and there can be fingerprints and there can be footprints. Fingerprints, you don't see with the naked eye. You have to have some technological enhancement to see the fingerprints. And what Mark was showing you this morning was the fingerprints of catastrophe. What we're seeing here are the footprints, the things that you can actually see in the landscape with your own eyes. And I think that the two now are actually complementing each other very nicely. Obviously, when J. Harlan Bretz and J.T. Pardee were looking at this stuff in the 20s and the 30s and the 40s, we did not have the type of technological enhancements that allow us now to see nanodiamonds, that allow us to see microspherules, to find iridium or platinum deposits and so on, right? So this is new stuff. But what it's showing to me is it's like providing a whole nother dimension of evidence that we can use to piece together these extraordinary events that have happened in the history of our planet. So here's the thing. When you look at this, it says Dry Creek Gravel Pit. The picture is facing southwest. Is there anybody out there astute enough to determine what the implications of that are? What? What did I hear? Yes. It's going these four sets are showing currents going the wrong way. Let's go back. Currents flowing southeast, not northwest. Now the current models are that all the flows were Lake Missoula draining outwards, so all of the flows would have been outflows, the draining flows would have been to the northwest. This gravel pit and others show southeast tilted or southeast dipping, to use the geological term, foresets. This is water flowing into the basin of Lake Missoula. Where is this water coming from? And in fact, there are rocks within those whose source is Canada. When I made that trip to visit Roy Breckenridge, who is no longer with us, died a couple of years ago, I went in there and I wasn't going to say what I was thinking, but he confirmed what I was thinking when he said he didn't really know about the ice dam, the efficacy of this model to hold in this massive body of water at those kinds of pressures. So I thought at the time, I think I'm on the right track. So the very next year, where do you think Bradley and I went? We went up into British Columbia and Alberta, looking for evidence that perhaps that was actually where the floods originated and not necessarily Lake Missoula. In the interim, what I've come to think of as Lake Missoula, and I still use the term because it's in the literature, everybody uses it. You say anybody who's studied any of this knows Lake Missoula, what you're talking about, even though at this point, I don't think it was an actual lake, okay? Let's keep going here. So, this is Okotoks, the big rock it's called. That's a flathead term. Okotoks is the name from the Flathead language. It means big rock. It's sitting on the western prairie on the Rocky Mountain front just south of Calgary. I think it was our trip up to see this where we first met and kind of allied with the Grimerica boys. Darren and Graham, I believe that's right. Anyways, we got a history that's going back now. They put us up while we were up here studying this stuff, actually served as our guides. Now, this is a metaquartzite boulder whose source was either Mount Edith Cavell or Mount Robson in Jasper Park, right? Here's another view of it where you can really see how big it is. And here's what's interesting about it. This particular rock was transported over 300 miles from its origin at Mount Edith Cavell or Mount Robson, that are both composed of the same type of gray metaquartzite that this boulder is. This boulder, you can see here it's cracked in two places, it's split into three parts, and actually you can see what's happening. If you look at the whole boulder, it extends underground here because it's relatively parallel top and bottom. But what has happened is the boulder has sunk into the ground, which almost certainly tells us that this was, at the time the boulder was deposited here, that it was alluvium, and probably alluvium that had not yet really hardened because it was soft. So typically alluvium is going to be laid down by flowing water. This, if you look at this, you can see very clearly the sharp edges, the almost 90 degree corners. Okay, what this tells you is it was not transported glacially. It was not transported typical glacial, because a glacier would have not transported a rock this big with this fragility, because you've got two major fractures within the rock. It would have been ground up, it would have been pulverized, it would have been dispersed throughout the path of the glacier. This rock had to have been transported via an iceberg. An iceberg most likely like the size of a tanker ship. The estimated weight of this boulder is about 18,000 tons. Now here's what's one of the things that when I learned about this, the Okotoks, the big rock, is that the source mountains, this is, like I said, Rocky Mountain front, this is Alberta, so it's on the east side of the Continental Divide. The source rock, the mountains that provided the source rock are on the west side of the Continental Divide. So now you have to contrive a scenario which you can quarry an 18,000 ton rock and transport it over the Continental Divide and then carry it another almost 300 miles and dump it in the western prairies of Alberta. How the hell do you do that? Well, I did talk to Warren Hunt about that. And without being too specific, he said this to me, and this is, I got to give this man credit. He's no longer with us, but I got to give him credit. He said, I think it was some type of a cosmic event involving an asteroid or a comet. He said that to me, I think we talked in 1996 or 97, before Bradley and I went on our first trip. However, I had read his papers in the late 70s. So I already had this idea, this testimony from him, that the whole idea of the ice dam was problematic, to say the least. And when I had this conversation with him before we embarked on our first tour out there, yeah, he confirmed. He's written a book, I don't know if it's still available, it was called Environment of Violence, where he goes into great detail. I was able to get a copy of it. He was selling it like personally, so being he's gone now, it may not exist, it may not be available. It may, somebody may have a copy online they're trying to sell. I don't know. But the two papers, I think I'm going to be, we're doing like what George did. I'm putting together, and Bradley is going to stay on my tail until we get this done. But on the website, we're going to do a full bibliography of all of the work going back to Brett's and all of the relative stuff and the various interpretations about the floods and what caused it, how the standard model that pretty much emerged that you will read in the popular press or the textbooks now, the dissenting views that have been accompanying that all along. There have been dissenting views. So anyways, this is part of what's called the Foothills Erratics Train or Athabasca Erratics Train, and this is the largest rock in that train. There's hundreds of them. They stretch over 500 miles. The south end of that train actually crosses the border from Alberta into Montana. And right there, you can see the yellow line is the border. And if you follow that train down, lo and behold, what do you see? A gigantic current ripple train. And these are extraordinary. That line right here is 1 kilometer long. So you're looking at wavelengths. Now these are shallow, but the wavelength, the depth again is going to be related to how fast the water's moving. So this was relatively flatter land in here, so the water's not moving as fast as the water that created Camas Prairie that I showed you earlier. But what you do have is this extraordinary wavelength where you've got over 1,000 feet of wavelength in these current ripples. Where do you think this water was going? It carved out the channel that is now occupied by the Missouri River. And you can see the current ripples right here going into Montana. And then if we go down here, let me skip that for now. Well, since it's here, let's talk about it. I was putting this together in a hurry, but this kind of will give you an idea. This is a cross section of the Clark Fork Valley just east of where the ice dam would have been. And I put the skyline of Atlanta in there just so you could get a sense of the scale. Okay, at the bottom of the valley, at that where the constriction widens out into the basin, it's 5 miles wide. At that 4,200 foot above sea level, it's actually 8 miles wide. So I managed a few years ago to find my way to the top of a tall building outside of Atlanta and get a photograph of the skyline. And now I've juxtaposed, now the tallest building in Atlanta is the Bank America building here, which is 1,050 feet tall. So as it turns out conveniently, that's half, the height of that building is half the depth of the water at the ice dam, right? So then what I did was I took and I plotted on maps where was 5 feet. So I took the center of the city right here. I went 2.5 miles north, 2.5 miles south at the bottom, and then 4 miles north and 4 miles south at the top. I juxtaposed that on my photograph here, and it will give you an idea of the water levels we're talking about here. This is an extraordinary phenomenon, and nothing throughout the entire Holocene has even approached this in scale, magnitude, or intensity. And that's why the features created by these phenomena still exist pristine virtually. Nothing in the last 10 or 11,000 years has been even close to being able to seriously modify these features. The giant current ripple fields look now almost as they would have looked 10,000 years ago. The great extinct cataracts, same thing, right? Once the spigots were turned off, those cataracts were left high and dry. They became fossil features, and there they sit in the landscape, almost in the same condition as the day the floods finally terminated. So we're going to go outwards a little bit, and what I want to show you here is just some of the cross-section of some of the literature that's available out there to give you an idea that this goes way beyond just the channel scablands of Washington. On the left, catastrophic flooding from Glacial Lake, Wisconsin. So, Bradley and I again have explored this in person, in the field. We found extraordinary evidence. I don't know if any of you from the Midwest have ever visited the Wisconsin Dells or have heard of it. Wisconsin Dells was the outlet for what they call Glacial Lake, Wisconsin. My criticism of Glacial Lake, Wisconsin is the same as my criticism of Glacial Lake, Missoula. I don't think it was a lake in the conventional sense of the word. And I can make a pretty strong argument because we can see the evidence that unlike a lake, there's evidence of current flow. Like in reality, it was a gigantic river of glacial meltwater. Now, Glacial Lake, Wisconsin, that meltwater would have been coming from the Laurentide, not the Cordilleran ice sheet, okay? Over here, a series of large late Wisconsin and meltwater floods through the Champlain and Hudson Valleys, New York State. We've not traversed or explored these yet, but it's coming up soon. One of the things that we like to do is we like to do a little recon first, because when we get 25, 30, or 40 people out in the field, we don't want to be driving around looking for something that we haven't investigated yet. So we like to investigate all of the sites first before we start taking people out. However, the door is open if anybody wants to volunteer to come and help do recons, which we usually will limit to a small number of 4, 5, or 6 people. And, you know, it's just a different approach. We cover a lot of territory. When we do these, the Scabland tours, we rent the Soap Lake Resort for a week, and we use that as our base. And then we make day trips out from there. It's a really great little place. It's cabins, a historic hotel. They pretty much open the doors to us and make it available to us. So that will be coming up, I guess not till next spring. Is that right, Brad? Next spring we'll do another one, but in the meantime we'll be doing, so the Montana tour and the Scablands tour are complements to each other. We try to overlap just enough so that you can make that connection, right? Because they're not two separate events. If we were going to try to cover both of them, we'd have to do the tours for 2 weeks, and we just haven't gotten to that level yet. Evidence for large subglacial meltwater flood events in southern Ontario and northern New York State. John Shaw, lead author on this one. John Shaw passed away a few years ago. We were actually scheduled to go out in the field with him, and about 3 weeks before, he passed away. And that was very sad and disappointing, because I had been reading his work for years. He wrote a seminal paper that I'm going to show you in a minute, co-authored by Jerome Lessman. I don't know how many of you guys have seen the Cosmographia podcast. We've had 2 on there where Jerome has come on to talk Drumlins. He recently has been working with Nick Zentner, who I've never met personally. I've seen some of his videos. And he's taken Nick out in the field and showed him some of the evidence. And I think Nick is coming around to thinking that maybe there's more to this explanation than just a giant lake that burst through an ice dam, which is gratifying to me, because a few years ago there was a number of people that would say, Randall Carlson, he has no credentials, he doesn't know what he's talking about. If you want to know the real story of Lake Missoula and the floods, look at Nick Zentner. And I always thought, Nick Zentner seems like a really cool, nice guy. I'd probably like to meet him someday. We'd have some very fruitful discussions maybe about the origins of these floods. But then when I found out, because Bradley and I have been out in the field with Jerome, and we've explored, I'm going to show you, because we're about to get into drumlins. Drumlins are one of the keys here to deciphering this whole thing, and how critically important they are, and what they have to tell us about these events, I think is mind-boggling. So anyways, John Shaw was an expert in drumlins, probably one of the foremost, but he came up with an outrageous theory for the origin of drumlins, which has been rejected mostly by mainstream geologists and glaciologists, who have maintained for decades that in some vague way, glacier ice somehow shapes the glacial till into these elongated aerodynamic hill-shaped forms, or aerodynamic shaped hills. Because let's picture what happens now when a glacier comes in. It's basically just pulverizing the ground mass below it. Pulverize it, breaking it up, leaves a stuff that used to be called drift back in the 19th century. It's now called till. Glacial till is the raw material that forms moraines. So you can have a terminal moraine that's at the edge of a glacier. You can have a lateral moraine that forms at the side of a glacier. You can have a medial moraine that forms where 2 glaciers meet. But the point is that these moraines are features that are constructed out of glacial till. Glacial till is a pulverized ground mass that's underneath glaciers, that's completely chaotic, that has no structure to it. However, drumlins are for the most part composed of glacial till, and they have structure, aerodynamic structure, and I'm going to show you pictures of them in a minute. And what Shaw theorized or hypothesized was that these drumlin swarms, or drumlin fields, if you want to call them that, were produced by water flowing under pressure under the glaciers. And it was because the water did not have a free surface, it wasn't able to adjust to its channel width by changing its depth. It had this overlying lid of thick masses of glacial ice. That meant that the flow was under pressure. And so because the water was flowing under pressure, it was able to shape the chaotic, maybe several hundred feet thick or even more, pulverized ground mass that we call till, okay? We're gonna see some pictures of that in a second here. We'll come back to John Shaw. Then over here on the right, we have geomorphic, sedimentary, and hydraulic reconstruction of a glacial lake outburst flood in northern Alberta, Canada. This is interesting because here's one of the things we begin to realize when we start studying the melting process is that you would think normally that, like, from glacial observations of the last 100, 150 years, what we've seen is that the glaciers that were swollen to their little ice age maximum 100 to 150, 200 years ago have shrunk back. They basically shrink back from their margins backwards, right? Upstream, up glacier. What we see with the melting of the ice masses at the end of the last ice age is that oftentimes the melting was far removed from the glacier margin, which has led me to coin the term melting epicenters, right? Because that's what it actually seems like. And when you have melting epicenters, and it's under, this water is moving under the glacier because you're not at the edge of the glacier, it's shaping the till into drumlins. Okay, let's keep going here. Glacial Lake outburst erosion of the Grand Valley, Michigan. Another big outburst flood coming at the end of the last ice age. How many of you have live in Michigan? Grand Rapids is right in Grand Valley. I know you are, Pat. Grand Valley, I'm going to show you a Google map of that in a minute. Here we go from Kehew and Lord, origin and large-scale erosional features of glacial lake spillways in the northern Great Plains. Their conclusion there that these were catastrophic meltwater flows. Outburst flood origin of the central Kalamazoo River Valley, Michigan. Gigantic catastrophic flows. Record of large late Pleistocene outburst floods preserved in the Saanich Inlet sediments, Vancouver Island. Outburst floods, right there in the terminology is the indication that we're talking catastrophic flows. River Warren Boulders, Minnesota, USA, catastrophic paleoflow indicators in the southern spillway of Glacial Lake Agassiz. I told the story earlier how standing on the edge of the big, deep 3-mile wide valley that the Minnesota River now flows in was kind of an epiphany for me. I didn't know then that it was called, that there actually was. Actually, the year on this, when was this? This was 2004. So my standing on that bluff looking into this valley happened decades before this paper was written. But later on, it was, I saw the actual research and it confirmed to me that the intuitive sense that I had was correct. And it turns out that the modern Minnesota River that flows in that valley, River Warren that he's talking about here, peak discharge was at least 4,000 times greater than the modern discharge of the Minnesota River. Sedimentary evidence of deglacial megafloods in northern Gulf of Mexico. Water being swept down from the north down to the Gulf of Mexico, built the entire delta that the city of New Orleans is on now. The catastrophic late Pleistocene Bonneville flood in the Snake River Plain, Idaho. This is an extraordinary event, not on the scale of Missoula, but it's extraordinary in its own right. We've done traverses of this flood from its origins of Lake Bonneville, of which Great Salt Lake is but a puddle left over. Lake Bonneville was nearly 1,000 feet deep from from the city of Salt Lake, Utah, north of there. If you look to the east on the Wasatch Mountains, you can very clearly see the shorelines left by this gigantic body inland, literally an inland sea. If you were sailing across it from one side to the other, you would not see the opposite shore. You'd be days sailing across this lake because it was literally a large inland sea up to, like I said, nearly 1,000 feet deep. So what we've done is we've started in the basin of Lake Bonneville and we've followed it all the way up to the inlet of Hell's Canyon and followed Snake River Plain. And there's some amazing phenomena along there. And Bradley just did that. Recently did a new recon of that. So we're planning at some point to do a Great Bonneville flood tour. And it'll be starting in Utah and going north through Red Rock Pass. We'll follow the Snake River Plain and probably get up to the mouth of Hell's Canyon. We're even looking into perhaps we could get a little tour in jet boats going up because Hell's Canyon is the deepest canyon in North America. And it's very possible that the final stage of deepening, and it's likely that the final stage of deepening was caused by the Great Bonneville Flood. And it ultimately, the Bonneville flood followed the route of the Snake River, which meets the Columbia. And there's a very interesting outcrop at Tammany Bar, south of Lewiston, Idaho, where the Great Bonneville flood met the Missoula flood. And that is a very interesting outcrop. I would like to take about 6 months off and just study. There's a gravel pit there that tells this amazing story. Because of time, there's so much that I had to leave out way more than I actually put into this slideshow. But again, we're covering a lot of this in detail in the Cosmographia podcast, and I'm going to do a series where I just take a section, put some concentrated evidence in it, and that'll be out for people to download, and I will start including a lot of these. We have thousands of images. We have probably hundreds of hours of videotape, and we're now getting a great collection of drone footage together. We've got quite a bit of aerial footage we've done. Okay, catastrophic flood hypothesis for the origin of Souris Spillway, Saskatchewan and North Dakota. On the right, the Kankakee Torrent and other large meltwater flooding events during the last deglaciation in Illinois. See, this could go on. Here's my point, is that to me, part of the problem is you have different, like, Kehoe and Lord, they've focused on the Midwest, this particular, what you see in North and South Dakota primarily. This next one over here, that's looking at what is now the Illinois, the Kankakee and the Illinois River. And when you look at this, you realize that there are these people looking individually at each of these individual events. But it's my contention that whether we're talking the Bonneville flood, the Missoula floods, all of the Kankakee torrents, these other catastrophic floods that seem to have occurred all over. Now we have evidence that there was a outburst flood path to the Arctic Ocean that carved out the modern Mackenzie River. So here's my contention. My contention is this, that yes, we've done a whole lot by individually identifying these gigantic flood features, documenting the evidence, but what has not happened yet is to integrate all of this. And I believe that we're not going to be able to understand these processes, the catastrophic flooding and melting, whatever was the trigger for this, until we start looking at this integrally and start looking into what is the interconnection between all of these gigantic flows that were coming off the ice sheet. And I don't think that normal melting is going to explain what we're seeing here. And when you spend some time out in the field going to all of these locations like we have, you begin to soon realize, it's almost, I feel like sometimes I'm in the Matrix, because we're living, the planet we're living on, and we can extend this beyond North America for sure. The planet we're living on top of the wreckage of a former world. I think Mark kind of said something similar to that earlier. When I show you a gravel pit, well, this is material that was ripped out of bedrock somewhere else, transported maybe hundreds of miles, and deposited. And half the time, most of the time, we don't know what's at the bottom of these huge, thick deposits, and we don't know what was sitting on top of the land before this material was ripped out and swept away, right? This, to me, is an extremely important paper, because what this does here now, it's connecting a catastrophic flood specifically with the timing of the Younger Dryas, which hadn't happened before this paper. And this is the paper of primarily James Teller has done this work. I'm gonna get into a little bit of Drumlins now so you can see what's going on here. We're not gonna digress to Mars right now, but here I want you to look at this and see if you can tell which direction from this is the water flowing. Lower right to upper left, if you guess that, you're correct. And you can see the craters, you can see the long tails in the lee side of the currents, right? Let's go to the next one here. This is another channel on Mars. And you see what's called a streamlined erosional residual. And here you had the flood bifurcate. It was originally, as I explained, it was probably started as a sheet flood, exploited a zone of weakness in the bedrock. Once it begins to downcut, it'll capture the sheet flow, and then the downcutting will accelerate. It'll leave the uplands high and dry at that point. So probably the latter part of the floods, this streamlined feature you see right in the middle of the channel here would have been an island. But let's come back to Earth. and learn about the principle of underfit streams. I've changed it to underfit rivers because I think that's a more accurate way of describing what we're talking about here. This was the work going back to G.H. Dury. It was in the 1960s, 64, yes, that he first began to realize that a lot of rivers in North America were flowing in channels way too big to have been formed by the modern rivers. So here's what he said in the introduction. In the customary but too restricted sense, an underfit stream is a stream that meanders on a floodplain in a meandering valley. Subsurface exploration proved certain floodplains to be underlain by large meandering channels, which were taken to be the channels of former rivers that carved the valley meanders. At each site explored, a large filled channel was located. Let's look at few examples here of underfit rivers. Snake River Plain. Take a look here. Modern Snake River, average annual discharge, 56,900 cubic feet. Bradley and I were in this airplane, fearing for our lives because the wind was gusting at 40 miles an hour. And I was hanging onto the strut there with one arm like this and the camera in the other. I do exaggerate. I was leaning out the window though. But you can see here, this is a beautiful example of an underfit river. And what you see here is that like it says up here, the modern average annual discharge is 56,900 feet. The estimated peak discharge of the Bonneville flood that cut this large channel, 40 million cubic feet per second. So let's just do something here. I'm going to take 40 million, put in my calculator, and I'm going to divide it by the average annual discharge, which is about what you see there now. And the answer is over 700 times the volume of the modern snake is what carved that channel. All right? And in the pathway of that channel, you find things like this. These are rocks that were plucked from the bedrock, transported some distance, and by the rounding of here, they're not spherical, as they would be if they were transported quite a ways, but you can still see they're basically rectilinear, but they are rounded. The roundness is going to be an indication of transport distance. So you see these two very large rocks here, and this gives you an idea of the power of the current flows of the Bonneville flood to pick up something like this and transport it. Here is an example of an underfit river from one of my very favorite books, Geology Illustrated by John S. Sheldon. He was a geologist and a pilot. This is a wonderful book if you can get it. So this is a textbook example of an underfit stream. Note the diminutive size of the modern stream in comparison to the channel it occupies. This is Cottonwood Slough in South Dakota, a relic of the glacial meltdown. And we'll go through here. You can see is two giant meltwater spillways converge about 4 miles west of Minot, North Dakota. Souris Spillway is on the right, Des Lacs Spillway on the left. If you look carefully, you'll see the modern river flowing in this channel. The modern river did not cut this channel. Okay, here's a massive streamlined erosional residual. You can see the channel. And if you look carefully right here, you see the modern river flowing in this huge channel. So this is an example of an underfit river. Okay, here's another one. This is the Illinois River, south and west of Chicago. Again, you can see the modern river is occupying a very large channel. Now here's the thing. Once you get that large channel and a river gets captured in that channel, it's stuck there. It's not going to rise up because these bluffs are a couple of 100 feet high. So unless the water fills up the channel up to the height of the bluffs and spills over, until that happens, it's confined to that channel from the point at which it's captured. Okay? This is the Minnesota River, and you see the ancient channel, the Meltwater channel, and you see the modern river. Here is the Wisconsin River west of Madison, same thing. The ancient channel, the glacial meltwater channel is huge compared to the modern river. Here's the St. Croix River channel at the Minnesota-Wisconsin border. And right down here off the screen, there's a constriction in the channel, which means you would have flow acceleration, which would lead to turbulence, and that causes this, underwater tornadoes, which produces this. This is a pothole. That's our good friend Graham looking down there, and there are potholes that are 80 feet deep. I don't know why, but I'm getting this intuitive sense that I'm coming to the end of the journey here. But I'll go through this super fast because the way we're going to leave it is, okay, just to give you perspective, here's the Missouri River flowing in its oversized channel. Don't go away. And here's a picture of the Missouri River flowing in that channel. So what's the takeaway from this? Yes, everywhere about us is evidence of gigantic cataclysmic flood flows. They're not confined to just America and North America. We find them all over the world. And I think that we really need to expand our thinking to the cosmic dimension if we're going to attempt to explain these kind of phenomena. And take this with you. When we build cities, we build high-rise buildings out of concrete. That concrete is composed mainly of pulverized limestone and gravels. Those gravels are coming from those are the leftovers from these great world-destroying floods that I've been introducing you to here. So I think there's probably some other things I'm supposed to tell you, but I don't remember what they are. But I think you're kind of getting the impression here. What we're trying to do now, and I didn't even get to the Drumlins, but so you're going to have to go to cosmographia.com, and I will teach you why Drumlins, I think, are the key to deciphering this whole thing. And when we get to that, we're planning some very cool trips coming up. I hope Johanna can.
I'm there, yeah.
You heard it, okay? And all right, thanks, I appreciate it. Okay, I have been informed that we are going to have
A Q&A.
a Q&A.
Yeah, we know you guys have been buzzing to ask Randall questions, so Q.
And Bradley Young had a good suggestion. He wanted me to tell everyone that this lecture will continue uninterrupted in 14 days on Asteroid Day, right? We're going to pick up.
Yeah.
If you're agreeable, but that's what Bradley said.
Here, twist my arm.
Okay. Okay, done.
It's done.
So Asteroid Day, we pick back up. Q&A now.
To try it, because I think the Drumlins are going to be, because the critics, one of the things they say over and over and over again, just like with the KT, well, where are the impact craters? And you know, this morning Mark was talking about Hiawatha craters potentially, but it looks like it's too old, but maybe not. But I'm going to show you some other possibilities.
Which side are we going to go to first?
Oh, I can't see what's going on out there.
This gentleman over there.
All right.
Randall, I had a question regarding what is the interaction with the water table, with that mega flow of water after, if you say it isn't a traditional glacial lake, is there a point where the water table just cannot absorb?
Yeah, I mean, it's going to be a function of the porosity of the substrate. So if you've got fractured bedrock, yeah, actually, pretty much, I think all of the North American aquifers were recharged during the meltdown. Certainly the Oglala aquifer, the big one in mid-western America, was recharged by the glacial meltdown.
And is there a point where that flow is almost, it's going slow enough where you're having almost like a secondary proglacial lake or a...
Yeah, I mean, what'll happen is once the ground gets saturated and can't absorb anymore, then you're going to have surface water filling up.
Okay, thank you.
Sure.
I was wondering how the... Yeah.
Oh, there we are, okay.
I was wondering, how does this increase in the interest in catastrophism re-examine von Daniken and Velikovsky's views?
Well, I think both of them. Can't say I'm not familiar with von Daniken, but I certainly did read Velikovsky back in the day when I was first embarking on this, probably even in the early 70s. Here was the thing with Velikovsky. I think there was two parts to his work. When he wrote Earth in Upheaval, he was collecting data from both the geological realm and the mythological realms that supported the idea that there were great catastrophes in recent Earth history. That was one part. The other part was he then went to try to contrive an explanation for him, and I think that's where he went off base. And most of his critics attacked the second part of his work, where he was essentially invoking an astronomical explanation that Venus and Mars were discharged from Jupiter, and the astrophysics didn't hold up, and he got savaged for that. However, his compilation of geological data supporting geological catastrophes and the mythological stuff, I think, has held up. So, yeah, I mean, you can read that, and most of what he was surmising in there, I think is, it was what was available in the 50s and 60s when he was writing and doing his research. But then, like I said, I think he went off track with his attempt to explain what was the forces behind this material that he had cataloged and documented. So, yeah, that's my take on Velikovsky, and I don't really have an opinion on von Daniken. Other than, I guess, when we get into the aliens and gods and all that, I do have an opinion, but that's not the subject matter of this conference. Later, we'll talk about that.
Thank you,
Yeah,
Randall.
what's next?
Thank you, Randall. I had a question. So I'm new to the Cosmic Summit group and loving it. Thank you for everything that you've put forward.
Okay.
My question is, what I've been picking up is that the water has been assumed to be here on Earth. Has any consideration been given to an ice comet or the water coming extraterrestrally?
Well, I think that, one of the ideas that's got a lot of support is that the hydrosphere was originally fed by cometary infall. I think that's, that to me makes a lot of sense. The water had to come from somewhere, and we know that comets are mostly water ice, or to a large extent. So, I mean, that's an idea, and I haven't thoroughly digested that information, but I think that that's a plausible scenario for where the water came from. Now, as far as the floods, let's say even if it was a 5-mile, 10-mile, let's say a 10-mile diameter comet nucleus that hit the Earth would not supply the quantities of water that we're talking about here. Because we're talking about, like I said, one filling and emptying of Lake Missoula was 600 cubic miles. And I think the volumes of water involved in all of these things that I've been showing you was many times that volume. So you have to come up, I think, with a way, the way you want to produce a catastrophic world-destroying flood is that you pile up 5 or 6 or 7 million cubic miles of ocean water, frozen, locked up as glacial ice on the continents, and then you come up with a way of really rapidly melting that. Now, if you think about civilizations, or the question of settlements, cultures, communities, whatever, when we look at sort of like what to me is the reoccupation of the devastated world in the aftermath of these events, where do we see the first cities forming and communities? Well, they're along waterways and along the coastlines. If we go back 15 or 20,000 years, I just showed you an example of the waterways. So if there was a waterway, a river, and it had a settlement, a town, even a city alongside it, you had a flow that came through that was 4,000 times the volume of the modern river. What's going to happen to that community that was built along that river? It's gone. No trace of it. What's going to happen to a city, a village, a community that's on the coastline that's now under 400 feet of water? What are you going to see? And you've got to bear in mind that rapid rising of sea level is going to create some pretty energetic surf phenomena that's going to easily erase whatever is there. So this is what we have to take into account when we start talking about what may or may not have been in prehistoric times. If we have no concept of these catastrophic events that have affected the entire world, we don't have a context for really even talking about that subject as to what may have occurred in the deep history of the human species on this planet that we now know goes back at least a couple of 100,000 years. And when you figure how quickly we rose from the pre-industrial civilization that we had to where we are now, 300 years. How easily could 300,000 years of progress get lost in 150, 180, 200,000 years of human history, maybe longer than that we modern humans have been occupying the planet? I think these are open questions. And if somebody tries to slam the book shut on that by saying that anybody who's raising these questions is a racist, white supremacist conspiracy monger, I'm going to tell them, get the out of here. So how's that? Okay, good. Next question, please.
Pretty simple question. The Atlantic Ocean, the name, sounds really close to Atlantis, and I saw some of your discussion about that. Do you know how long the Atlantic Ocean has been known as the Atlantic Ocean?
Well, it was certainly known in Plato's times.
And is that by the naming convention that the entire world uses now for the Atlantic Ocean is its own type of proof of the Atlantean
Well,
Empire?
I wouldn't say it's proof, but it's very tantalizing evidence because, you know, bear in mind now, think about the letter C can be hard or soft. It can be a fricative, which is the back of the, like if you say, think of the word, let's think of a word that starts with C, a hard C. What? Cosmic. I'm looking for a word that has both a hard C and a soft C. Circus, okay? You've got circus is a soft C at the beginning. The second C is a hard C. So a fricative, let's see, a fricative is when the tongue is at the back of the teeth when you're making a hissing sound. But in olden times, the Atlantic Ocean was the fricative. So, I mean, it was pronounced with a soft C. So it was literally Atlantis Ocean. So, yeah, hopefully that's suggestive to me.
Yes, sir, thank you.
Yeah. What's next?
I've got 4 hard questions, but I'm going to give you just one easy one.
Okay, yeah.
You know the Carolina Bays?
The term what?
The Carolina Bays? Those things? The circles?
I'm not sure.
Carolina Bays.
Oh, the Carolina Bays, okay, yeah. And what about it?
Okay, couldn't that be like where the Anunnaki took off? From here before, because look, it spins
I don't know. That's
like
an awful
this.
lot of. I mean, what do we say that there's 80,000 of them? Where's?
But what if that was their helicopter pad, kind of, because they go like this, and then it makes that circle and the lip, and then it's water and it's magnetic. All that fits. Anyway.
I'll have to take that one under advisement. I don't know, was that was the easy question? I'm afraid what the hard questions were. All right.
Hey, I just wanted to first say thank you for the Cosmic Summit. This is awesome.
Well, I just showed up. George did all the work.
Well, George, I appreciate you. And I had 2 quick questions. First one is about the moon.
Yeah.
You know, it's sitting there in the background behind you. And I can't help but notice that all the craters seem to have like a similar depth.
Mm-hmm, yes.
Well,
Okay, you noticed that, yes.
So,
and?
so I was wondering if you could give me some insight on how you feel about that and what your impressions are. And then my second question or ask of impression is there is another YouTube channel called Suspicious Observer.
Yeah.
Ben Davidson.
Yeah, I've been on Ben's show a couple of times.
And he is very convicted in his idea about how the next 20 years or so are going to play out with solar micronovas and more.
Okay.
And I was just kind of interested in what your thoughts on
I would have to get with Ben
potentials
and
ideas are.
I would have to get with Ben and hear hear his thoughts on it and, his arguments in favor of that.
I thought you did spend some time talking to him, so I was kind of.
Oh, well, I have, but I mean, I bet you the last time I talked to him had to have been 5 or 6 years ago.
Yeah, 4 or 5 years ago.
Yeah. So.
Just kind of interested in what you thought about solar micronovas and what you think about the very seemingly shallow, flat craters on the moon.
Okay, well, we will say this. Regardless of the width of the craters, there's a typical width to depth ratio in cratering phenomena. You can figure that on very roughly, the crater would be 10 to 20 times as wide as it is deep, right? So when you look at, say, the crater out by Winslow, Arizona, it's 1 kilometer wide, 600 feet deep. It's going to be close to what you would expect. And of course, that's going to be a function of the density of the substrate, that is the target rock, the density and velocity of the projectile, the angle at which it comes in through the atmosphere. So all of these things are going to affect that width to depth ratio. And what you see on the moon is up to 30 miles or so in diameter, that width depth ratio tends to hold, and then once you hit about 3 miles in depth, the craters continue to get wider and wider and wider, but they don't get any deeper.
So 30 miles in depth tends to seem to be
Well, craters are not 30 miles in depth.
I'm sorry, 30 miles in width.
You would, yeah, so you figure 10 to 1 ratio, so you got 3 miles deep. But then when you get to the bigger craters, they're so shallow that if we're standing at the middle of the crater, you would not see the huge mountains that form the uplifted rim.
Well, I imagine that's due to.
What do you imagine that's due to?
Well, I'd imagine it's due to the curvature of the moon.
Well, yes. Absolutely, it's because of the sphericality of the moon, which, by the way, is not perfectly spherical, and that itself tells us a few things. But yeah, I was not going to get into a in-depth discussion of the moon tonight.
Well, I was just trying to push your buttons a
People
little
have been trying to push my buttons for a few months now about that, and there's going to be a signal that I get when I know the time is right.
Who gives that signal?
That's the problem. I'm not sure yet where that signal is going to come from, but I'll know it when it gets here. But one of the things is the Artemis project is underway now. So I realize that since we're now planning a return to the moon, that the time is coming up very soon to delve into that. And I've avoided it up to this point for various reasons, because it gets pretty outrageous, to be quite honest. Although if we recall the words of the great William M. Davis, who was the founding father of geomorphology, he wrote a paper in 1926 entitled "The Value of the Outrageous Hypothesis," because he was getting tired of all of his colleagues being so constricted and hidebound in their thinking that he wanted to shake things up, and he said there is a role for the outrageous hypothesis. And this, what you're asking about, leads us to really a very, very outrageous hypothesis.
I understand.
So I don't like to really talk about things until I'm fully prepared. It'd be just like this. If I was an MMA fighter and I'm going to step into the ring with a champion fighter, I'm going to make damn sure that there's no holes in my game and that I know what the opposition is going to throw at me. And I'm very, very close to that. But there's a few holes in my game, questions I still have that need resolution.
Well, I hope that when the time comes,
it's coming,
whether you have holes in your games or not,
that I'll go in there and get my ass kicked? Is that what you're saying?
I hope you're still ready to fight, because we need you.
Okay. But actually, Bradley and I have been planning a disclosure strategy. So it's in the works, my friend. And hey, I could be completely off base with this thing.
That's okay.
But then again, maybe not. So we'll see.
I got a question. Oh,
Okay.
Not me, asking for a friend.
Okay.
From the live stream. Michael Wright says, what was the duration of the flood events? Did the geological changes occur over hours, days, weeks, months? How quickly did the water source deplete?
Victor Baker, who did the work that I quoted that he published in 1973 in Rathdrum Prairie, and others have estimated that some of these peak discharges only lasted from a few days to a few weeks. Now, the Bonneville flood lasted about a full year. It was slightly different because in the Bonneville flood, of course I've got the slides and the maps and everything, but I don't really have the time to get into pulling all that up, so we'll have to save some of this for the podcast or wherever, the next conference or whatever we do. But if you go and you look at the Great Bonneville, Lake Bonneville, huge, huge area, inland sea, there's a narrow constricted outlet to the north called Red Rock Pass. What you had there was you had granite bedrock that was very hard and dense, and on top of that you had about 300 feet of softer sediment rock. Sometime around between 11 and 15,000 years ago, the dates are still imprecise, we need better dating, it may have been concurrent with Missoula floods, maybe not. Some of the studies would suggest the Bonneville flood was older. By how much, we don't know. That's why the Tammany Bar outcrop that I mentioned earlier I think is so important. But anyways, if you can picture, the water rises up, spills over a rock, a sedimentary rock dam at the northern outlet of the lake. And in our flood tour, Bonneville flood tour, we go through that pass and we point out everything so you can see the type of rock, you can see the remnants in the pass. But the water flowed over the rim, over the sill. Because it was a softer rock, it rapidly ate down through that 300 and some feet of softer rock. And then when it hit the hard granite sill, it stabilized, it stopped, right? So it took based upon the volume of water that was the whole area of Lake Bonneville, 300 and some feet deep, moving at the rate that I showed you there, which was about 40,000 cubic feet per second, 40 million cubic feet per second, it would have taken about 1 year for that water level to drop the 300 plus feet. Then when it hit the sill, it stabilized and it had no more outlets to the ocean. So what happened is with the onset of the Holocene and the oncoming warmth, post-glacial warmth, that remainder lake began to evaporate away until all that was left was the modern Salt Lake, right? So think about that flood taking about a year for that volume of water to drain. Now, but this is not water that's coming directly from glacial melt. Glacial melt may have been contributing to it, but it was undoubtedly a very much rainfall falling over that basin, the basin that is now Great Salt Lake. Then you've heard of Bonneville Salt Flats. All of that is the mineral material left over from the evaporation of the lake. That took about a year. So glacial meltwater flows coming off the rim of the glaciers, they probably lasted from a few days to a few weeks. Now the question is, how many times was that process repeated? And this is where it gets into sort of more complex than we can deal with here. Because our problem is we have to get to where we have 6 million cubic miles of ice piled up on the land, and then we have to it's got to be gone. It didn't all happen at once. So there's a lot of work that still needs to be done. So if you've got youngins that are interested in geology, see, when I was a kid, the thing that I loved geology, but it just, every textbook and everything I read or heard, it's like one grain of sand and one drop of water at a time. And to me, when I'm like 12 years old, it just seemed really boring, So later on, when I discovered, no, wait a minute, there are times when that rate of change gets seriously interrupted and things get really exciting for a while. Okay, that's when I really started getting interested in geology. So I hope that answers the question, Johanna. Okay.
All right. Randall, I live in Fort Wayne, Indiana, on the moraine that was left by the Erie lobe of the Laurentide Glacier. And they call it the Summit City because the water flows from there up out through the St. Lawrence Seaway.
Yeah.
If you go just a little to the west, the Little Wabash continues down through the Mississippi to the Gulf.
Yeah.
Have you examined what the flow, catastrophic flood flow, might have been like in the region where I live?
Oh, yeah. The Mississinawa, you can see the evidence all in the Mississinawa, I believe, was a tributary to the Wabash. The Wabash was a tributary, to the Ohio, I believe?
Yes.
Yeah, if you traverse those rivers, you will see evidence of major meltwater flows along those conduits, for sure, absolutely. Let's see, I didn't pull up some of the papers that have been written, but yeah, papers have been written documenting catastrophic floods all across the Midwest, Illinois, Indiana, Ohio. I have a paper, if we'd have kept going, I could have showed it to you, where they're documenting that the depth of the water flowing through the Ohio Valley was about 200, I believe, and 60 feet above the modern floodplain. And deposited, if you go dredge down on the bottom of the modern Ohio River, you'll find a gigantic boulder bed at the bottom. So, all right, next question.
First off, I just wanted to give you a huge thank you for all that you do and all the knowledge you've shared. You truly are an inspiration. I was curious. Now, we seem to be establishing a pretty plausible explanation for the cooling that we see at the beginning of the Younger Dryas. What do you view as the most plausible explanation for the major climate oscillations that we see throughout the whole of the late Pleistocene previous to that?
Well, there we go. And quite frankly, I would be misrepresenting myself if I really put forward any. I don't know. That's the answer. The answer is I don't know. Like Mark said this morning, what happened at the end at 11,500 or 600 years ago, when it was probably even faster than the beginning? Before I even tackle the older ones, I'd like to know what happened at 11.5 and what happened at 14.6. It seems, though, like there's roughly a 1,300-year interval between each of the three events. The 14.6 to the 12.9, the 12.9 to the 11.6, to use round numbers. So could that 1,300-year interval have anything to do with it? Well, possibly, if, again, referring to Mark's lectures this morning, if you've got the torrid meteor stream, and I'm going to break this down further in the Asteroid Day live stream that we do, looking in much greater detail at the breakdown of the comet, the giant, and Comet Encke that Mark mentioned this morning was undoubtedly an offspring of the gigantic progenitor comet that began to undergo a hierarchy of fragmentations and littered the inner solar system with cometary debris. And he used a really good analogy that I've used, that I think of it as a racetrack, and you've got a road going across the racetrack, and you've got a cluster of race cars going around, really fast, and then you've got this road cross-cutting, and if you're driving, if you cross the track when the cars are at the other end, you'll get by okay. But if you cross the track when that group of cars is right there, you may very well have a collision. And I think what happens is you have collision, or what has been referred to as impact epochs, where cyclically Earth may move through the byproducts of a disintegrating comet, and there may very well be a cyclical nature to that. But that's something we'll be exploring in greater depth during the June 30th. So join us for that, because June 30th, again, like I said, 115th year anniversary of the Great Tunguska event of 1908. And some of the stuff that Mark, I don't think, got into was, like, for example, some of the genetic anomalies that seem to have accompanied that particular event, and some of the other very, very bizarre and interesting phenomena that, if you had a multiple impact event, would have been orders of magnitude even greater. Species that showed up that had never been seen before is an example. So we're going to try to get into that a little bit more on Asteroid Day. So, all right, next question.
I'm still Richard Howard, and the last gentleman kind of stole my thunder. That I'd really appreciate you being here, and most of us have read you and never seen you live in action, and you're not like the picture.
No?
No, you're better.
I'm far more dynamic in person? Okay.
Yeah, we like the real deal. other
Okay.
than the words.
Well, wait a second. What's the problem with the picture? Hey, you haven't seen pictures of me 40 years ago, okay?
Okay, right?
We'll do a slideshow just on that someday.
Okay, full house.
Okay.
My question is
you have a question? All
yeah,
right.
got a question.
Okay.
The Salton Sea. It is the armpit of the Coachella Valley.
Yeah.
It's down below Indio,
Yeah.
Thermal, and Coachella. And it was a thriving resort in the 30s and 40s.
I seem to recall something about that.
And it's the most creepy place you could ever be.
So you're saying we should do our next conference there?
Yes.
Okay.
Get you a good deal. Something eradicated all of the existence around this lake.
I mean,
And
since the 30s, you mean?
since the 30s.
Okay.
And it flows into the Gulf of Mexico. And it totally dried up, dead fish all over the embankment, no water in there.
Okay.
And it might not be your deal.
No, it isn't. I
Salton
haven't
Sea.
looked into it. I've
Yeah.
certainly heard of it. I'm familiar with it. I know it
Right.
died.
Yes. It
Beyond that, I haven't looked in to find out why it died.
Right.
So, Richard, I'm going to give you an assignment. You got to do some research and get back to me.
Okay.
All right.
I think the pollution coming up from Mexico did it, but I'll do a little more research, Doctor.
Okay.
Thank you.
All right.
Salton Sea.
Greetings, Randall. My question is, you talk about the isostatic movement of the Azores Plateau.
Mm-hmm.
Does that apply to something like Reelfoot Lake at the New Madrid seismic zone where 1812 Reelfoot Lake sank?
Yeah.
And then the Mississippi River flowed into it.
Mm-hmm.
Can you?
Well, I think, the New Madrid zone was probably destabilized by the supercharging of the groundwater in there and the isostatic uplift to the north. One of the things that is now known about when you have large glacial masses, it'll push down under the glacier, but around the perimeter of the glacier, it lifts up. It's called the glacial forebulge. That glacial forebulge would have been all in that region south of the Laurentide ice sheet. When the Laurentide ice sheet melted, you had the uplift of the land, and under the glacier and around the rim, you had the downwarping. That downwarping, or residual downwarping, I think very well could be why you had that New Madrid earthquake right there. But again, there's a lot of things to know and study, and I like to create the impression that I know everything. But to be honest, I don't. Give me another couple of weeks, though, and no. No, there's a lot to learn. That's why I'm really hoping, I want to see a new generation of scientists come up who are willing to look at our own past and history of our planet and our species on this planet with an open mind. I think that's critically important at this stage, because there are really a lot of unanswered questions. Even though the authorities would like us to all believe that they've got everything all figured out, and all we need to do is accept anything they tell us on faith, which I totally reject that notion. Okay, next.
So you dangle this carrot out in front of us about the vast amount of energy it took to melt the ice sheet to create all this water. But you didn't really say where it came from.
No, we didn't. However, within the context of this conference, I think you should be taking away a pretty solid idea of where I'm going with it. And what we didn't have time to do was get into what I said I think is the key to this, which is the distribution of the great drumlin swarms over North America and over northwestern Europe as well. And since we're into this, can I show you something very quickly about the drumlins? Well, good. Okay. So let's go here. Now this is Lake Ontario, right? Now let me see where if I've got this. Oh, I'm in Google Maps. Okay, so I'm not in the slideshow. I want you to look at this. Here's the Finger Lakes. I want you to notice these Finger Lakes. Now what I'm going to do is I'm going to zoom out and look at like Lake Seneca here, it's about 25 miles long, and it's very deep, right? It's filled with water. It's typically 1 mile to 2 miles wide, and in some places over 1,000 feet deep. Now I'm going to scroll out, and I'm going to go over here to eastern Washington, and I'm going to scroll in on upper Grand Coulee, which is about 1 mile wide and about 800 feet deep. And as soon as there we go. I want you to look at this, and I want you to compare that to Lake Seneca and Lake Cayuga. I would submit that they were both formed similarly by catastrophic flows. Both Grand Coulee is now accepted to have been a catastrophic flow, but there's no consensus when you go over here to the Finger Lakes that they were produced by catastrophic flows. However, there is evidence that they were. And I don't have those papers handy here. We will get into that, and we may even have to get into that a little bit on Asteroid Day. But one of the things I want you to notice here is that if you look at these lakes, from like starting up here by Oneida, and you come around, you should notice that they're radially distributed. You see that? If you follow these axes of the lakes, and then you come over here, if you draw lines along the axes of these lakes, like I have done, they converge right here on Rochester Basin, it's called, which is the deepest part of Lake Ontario. Now, if we zoom in, now at one point, the glaciers apparently came all the way to the bottom end of these lakes and formed and basically pushed up against the flanks of the Adirondacks here. Okay, so now the glaciers receded to the north end of the lake, and then between the lake and the top ends of the Finger Lakes, between Lake Ontario and the top end of the Finger Lakes, I'm going to zoom in here, and then I want you to see what reveals itself as I zoom in. This is a drumlin swarm. This is what John Shaw theorized was formed by gigantic, highly pressurized subglacial floods. And we can come across here and we will see that there are thousands of these elongated, aerodynamically shaped hills. And if we come over here, we can keep coming over here, and when we do, you'll notice the orientation of the drumlins is changing, because the drumlins, like the Finger Lakes, converge on Rochester Basin. Now, how would you explain gigantic, highly pressurized subglacial floods flowing under the ice sheets, discharging from the ice sheets, carving deep channels that are now filled with water, and they all converge on a central deep basin? How might we explain that? Given that at one point all of this is under ice, right? What do you think?
Now go east.
Could it be that Rochester Basin, right over here, you've got to come up, remember I use the term melting epicenters, right? If this is a melting epicenter here, how do you produce a melting epicenter? What's one possible way? A strike? I would say that would be candidate number one. Yes. And I should actually pull up one more thing to show you this. I can't leave without showing you guys this. Oh, there's my old friend C. Warren Hunt, first published geologist in 1977 to propose an extraterrestrial trigger for the Missoula flood. His work has been completely ignored by mainstream geologists. So that's C. Warren Hunt, but that's not what I was going to show you. I'm going to show you, let's see. God, I got so much here we didn't get into, but don't worry, we'll be able to get into all of it. Let's see here, where did it go? Maybe I didn't put it in here. If I didn't, I'm sorry, but we can get into that on Asteroid Day. Oh, I'm not in the right. It would help if I would get into the right PowerPoint show. Okay, sorry about that. Just bear with me a second here and I'm going to show you something. Here is why I think that glaciers are not going to work to ice dam. Here's what I've taken is just a couple of examples. Now, these are typical outburst floods like we've documented within the last 100 years. I could have had 20 or 30 examples like this that are going to be similar. So here's a section profile of Lower Salmon Glacier and Summit Lake, vertical exaggeration 2. Now, I want you to look at the average depth of this lake. Now, this is the average depth at which point the ice dam fails, 140 feet. What was the depth of the water against the ice dam for the Lake Missoula? 2,100 feet. Okay, look at this. The volume of the lake, 0.04 cubic miles at the point at which it burst through its ice dam. So what I'm going to do is I'm going to take 600 cubic miles, the volume of Lake Missoula. I'm going to divide by 0.04, and that will give us the ratio of this lake to Lake Missoula. And Lake Missoula was only 15,000 times greater than this Summit Lake when it burst through its ice dam. Well, let's look at estimated peak discharge, 40,000 cubic feet per second. I'm going to use Vic Baker's estimate in Rathdrum Prairie of 752 million cubic feet per second. I'll divide it by 40,000, and it tells us that the volume, the peak volume, measured volume of the outburst flood from Lake Missoula was only 18,800 times greater than this. Okay, let's look at one more just so you can really get it. Okay, look at this. We've got volume of lake 0.003. So I'm going to put the 600 back in. I'll divide by 0.003, and the answer is that the total volume of Lake Missoula was only 200,000 times greater than this lake when it burst through its ice dam. This is why I question the efficacy of the standard model, right? Let's look at total estimated peak discharge. Again, I'm going to put in Vic Baker's number of 752 million, and I will divide by 15,000. And the peak discharge of Lake Missoula, the biggest measured discharge of Lake Missoula, 50,000 times greater than this. Do you think it's reasonable to question the whole ice dam theory, given what we're seeing right here? And I could multiply these examples by dozens. And here you can see, I ask, a half-mile high dam of glacial ice holding back a 2,000-foot deep lake with basal pressures in excess of 950 pounds per square inch. Is this realistic? Could this have happened over and over again from 40 to 90 times? I'll let you be the judge of that. But I just want to show you some photographs of the architecture of temperate glaciers, and ask yourself whether something with this kind of structure could actually hold back 950 psi. And again, we're going to just skip over some incredible stuff here, and I'll show you some aerial footage of drumlins. This is what a drumlin looks like from the air: a blunt end, which is upcurrent, a tapered end in the lee side, which is the downflow. So a drumlin is a paleocurrent indicator. It'll show you which direction the water was flowing. And what I'm going to do here is I'm going to show you, let's see. Oh yeah, here's a good one. This is a great photograph right here of a drumlin, a forested drumlin up in Saskatchewan. Now, once you begin, and this is what I'm saying, is that I think the drumlins are critical to deciphering the mystery of what happened at the end of the last ice age that caused the gigantic floods, the deglacial melting, the mass extinction, and I think that the most likely explanation would have to be a multiple impact event, okay? But then the question is, where did the impacts occur? This is a good graphic because it shows the Rochester Basin, and what happens is when you project those radial lines from both the Drumlins and the Finger Lakes, they converge right on the deepest part of Rochester Basin. And how many of you have ever spent time exploring the beautiful gorges up there by the lakes? They're amazing, they're magical. You'll see what you got right here, though, is a gigantic 10-foot diameter pothole. The water, the 6 or 8 or 10 inches of water flowing over this bedrock floor did not create this pothole. And all throughout the South, these are pictures that were taken. You see this kind of stuff. If you venture off the main routes and go up into the creek valleys, you're going to start seeing stuff like this. And this is what I was talking about earlier. We're looking at literally the wreckage of the former world. And it was extraordinarily intense, powerful, violent events that did this. This is what's called an imbricate boulder. This is also a paleocurrent indicator. Flow would have been from left to right. Potholes, you see this when you see the giant boulders, when you see the imbricate boulders, when you see the potholes, you have to look at these as a suite of features that were created under conditions that are no longer operational. Look at these boulder deposits that are along the flanks of the Cumberland River, right? Look at, now this is imbricate boulders. Look at this, as you can see this. The tilting of these rocks points, you see the arrow here? Picture you've got a bookshelf and you push on at one end and the books tilt over in the direction of the pressure, right? Same with imbricate boulders, right? So here you've got imbricate boulders. They are very much an indication of large flows, and they're very much also an indication of which way the water was flowing. But now look at these imbricate boulders. The next slide will give you an idea of the kinds of paleocurrents to which the southern Appalachians have been subjected. You can barely see them, but they're there. Look at the size of these boulders, and then think about the current flows of water that would have moved these boulders. Now this is not from direct glacial melt-off, so what's it from? I want you guys to think about this. Snake River Plain. You can look, remember I told you about the rounding of boulders is going to be an indication of distance of transport, right? So this is a 3-mile, hundreds of foot thick, gigantic boulder bar left in the wake of the Great Bonneville Flood. And then we get to this kind of stuff where digital elevation maps are showing the scale of these phenomenal flows. Look, this is Lake Superior up here. This is Minnesota. Here's North and South Dakota. We're looking at flows that are literally almost as wide as an entire state. And these flows went south, flowed into the Gulf of Mexico. And this you see oftentimes right there on the nightly weather report. And nobody seems to get it. Nobody seems to notice, well, what's right in front of your faces here is you have this gigantic streamlined form where you had a huge current coming down. It's split right at this point. And when we go north of there, we can begin to see these gigantic flows. Here you have streamlined erosional residuals that would have been islands at the later stages of the flood, but you can see where these tremendous floods swept down from under the ice sheet and then basically flowed into the world's oceans. And it is evidence like this that I think we can now begin to identify melting epicenters. And those melting epicenters, I think, are the clues to where impacts actually would have occurred on the ice sheets. So I get into the cosmic trigger. I'm going to save that for our June 30th. And I'll do one more thing if you want me to, otherwise I'll take a couple of more questions, but I think this answers some really interesting possibilities. I'm going to go through this really quick. Okay, this was a paper published in 2013. One of the authors, Malcolm LeCompte, he was, if you ever saw the great debate on the Joe Rogan show, Malcolm LeCompte was the fellow we brought in. He was also one of the primary people that debunked the debunkers. But what this does, this study, they were looking at microspherules like Mark talked about this morning. The Younger Dryas boundary site in Pennsylvania is remarkable in yielding 2 to 5 millimeter diameter spherules containing minerals such as swaycite, which is iron nickel silicide, that form at temperatures in excess of 2,000 degrees centigrade. Gross texture, mineralogy, and age of the spherules appears consistent with their formation as ejecta from an impact 12.9 thousand years ago. And then we'll jump down. This study ties the spherules recovered in Pennsylvania and New Jersey to an impact in Quebec about 12,900 years ago at the onset of the Younger Dryas, okay? Now, Quebec, but where in Quebec? Turns out that the precise location is right here, let's go back maybe, was, yes, here we go. The spheroids indicate that their source lies in the 1.5 billion Quebecia, if I'm pronouncing that right, terrain in the Grenville province of northeastern North America. So you have these spheroids that came down, raining down over Pennsylvania and New Jersey. Their geochemistry indicates precisely where they came from. It's in this small little area of Quebec called Quebecia, and I'm almost done, we look at the map, and there's Quebecia right up there. I'm going to zoom in, and there's Quebecia right there, and I want you to look right where that red dot is. And when we go to the next slide, what do you have right there at that red dot? Look at this right here. And you had a catastrophic outflow to the southeast right here into the St. Lawrence Seaway. And I would submit that this might be a prime candidate for an impact site onto the ice sheet right there. And in this limited terrain is where you find the geochemistry that's consistent with the microspherules in New Jersey and Pennsylvania. So we'll leave it there.